Time would not wait for others. ऑफलाइन होते असं बोल नाही मोठं असं चालू सर लाइव स्टार्ट होतं
A very good morning to one and all present here. Today, I, Dr. Sharma, once again welcome you all in AMSE 2024 Day 3. For our first technical session today, the session chair is Professor O.D. Markinde, and our first keynote speaker is Professor G.T. Rajashekar. He is in the Department of Mathematics at Pradesh. He has more than 27 years of teaching and research experience. His research areas are on mathematical modeling and applications of fluid flow problems to real-life problems like biological tumor growth and drug transport, existence and uniqueness result, dynamics of swimming microorganism, multi-phase models to enhance oil recovery. He has been recipient of several prestigious awards and fellowships, like Indian National Science Academy Young Scientist Award, Alexander von Humboldt Fellowship. He is a fellow of National Academy of Sciences, Andhra Pradesh Academy of Sciences, West Bengal Academy of Sciences. He was awarded the JBS Gold Medal by Indian Academy of Mathematical Modeling and Simulation in the year 2018. He was awarded the National Mathematician of the Year 2023 by Konala Trust Instituted at National Institute of Technology, Valedictory. He is also serving as an Associate Editor of Journal in Engineering Mathematics and the Managing Editor of Journal of Differential Equations and Dynamical Systems. With this, I request him to please begin with his.
Okay, no problem. So, good morning everyone, and thanks to the organizers for giving me this opportunity. Okay, so applied maths in science and engineering, so that's the title. So therefore, some small piece of works we thought I will introduce to the audience. Okay. So once again, this is my first visit, even though we have a number of colleagues flood from ITER to here from math department. This is my first visit, and thanks to the organizers. So the title of the talk is Some Applications in Computational Modeling. So the need of the computational modeling is almost like the parallel laboratories, because if you want to conduct experiments in certain areas, it's very difficult. So you won't be able to do a physical experiment, a particular experiment. So therefore, using math, you have to develop a lot of scenarios so that you get some idea, and then use those closest scenario to the experiment grid of this room and come to an estimate. So there is no escape. So computationally it is very expensive. On the other hand, even if your operator is linear, you want to solve very irregular geometry, then also you won't be able to handle analytical solution. So you have to go for a numerical solution, right? So I'll introduce a method where you can improve the computational cost. In which sense? Suppose your domain is 2D, using finite element or finite volume, you have to discretize method or anything. But I am telling you, just with discriminations, we can obtain the solution. Okay. So what are the advantages of this method and disadvantages of the method, etc. If you see, I already spoke. You require something called free space Green's function or fundamental solution of the operator. So if your operator is nonlinear, you don't have this. So therefore, you will be able to use this method. Whereas if it is linear, so then it can handle arbitrary domains. Okay. So that's the advantage and the disadvantage I mentioned. Okay. So those who are not familiar, so I just want to give you a feel of what is a free space Green's function. So for example, if you take Laplace equations, which are generated due to derived delta function. So at r equal to 0, okay. So it's not a classical sense, it's in distribution sense. Okay. So this is a tool that we require to develop this boundary integral method, right? So I thought I can derive, but I will not. So those who are interested, you can see these are the Green's functions of linear operators. So many. See, this is for Laplacian. I know this is Helmholtz equation, which is in terms of Bessel functions. Modified Helmholtz equation. So then by Laplacian. So these are the Green's functions. So all of these operators as a boundary value problem we can solve for irregular domain very effectively. So if you use finite element method or finite difference method, what is the constraint? Suppose you imagine this as a grid. Between each chair one line, then between each row one line. So now you have a grid structure. Somebody wants solution at the middle of the seat. So P indicates the location of the source where you are taking the singularity. So now what are the possibilities? Singularity is interior to the domain. Singularity is on the boundary. At a non-smooth point, it's like a kink with an angle alpha. So like you can see onion, so the singularity is located at the tip of that. Okay. So accordingly, the coefficient, so we can derive this boundary integral representation. Okay. So if the singularity is located interior to the domain, this coefficient is 1. If it is half, if it is outside 0, if it is at the kink, alpha by 2 pi. Okay. So how do we, so what it is, using the Green's second identity, we derive the boundary integral representation. So due to lack of time, I am not showing the derivation. It's a standard derivation. So now, this is alternative to your finite difference method. How? It is saying by fixing the singularity location, I can get the solution at any point. And what is the requirement? We know the Green's function and derivative of the Green's function. Then what is missing? Function value and derivative of the function on the boundary. But as you know, suppose you are solving Laplacian, what is the Dirichlet problem? Only function is given on the boundary, derivative is not given. If it is a Neumann problem, derivative is given on the boundary, function is not given. So, for each, you have to first find the missing data and then solve at any interior point. First find the missing data on the boundary and then solve at the interior point. Right? So there is no goal. So how do we solve it? So let me explain. Suppose you consider a Neumann problem. Then what is given on the boundary? Dou psi dou n is given. So now what is the unknown? Unknown is psi. So unknown is, and it is, what equation it is? It's not differential equation, it's an integral equation. What I am saying, Neumann problem, this is known. So it's an integral equation. What kind of integral equation? It's a Fredholm integral equation. Because we are working on closed boundary. Then it is the first kind or second kind. Since the unknown is sitting outside, it's a Fredholm second kind. So all that you have to do is you solve a Fredholm integral equation. and rich theory is developed for Fredholm integral equations. Right? On the other hand, suppose it's a Dirichlet problem. Then what is given? Psi on the boundary is given. Then it will be an integral equation for dou psi dou n. And it is a Fredholm first kind because just integral d dou psi dou n, the rest is known for you. So, depending on Dirichlet problem or Neumann problem, first you solve Fredholm first kind or second kind to obtain the missing data on the boundary. Once you get the missing data, how do you get the solution in the interior? I will go for first time, I will go for this. First time I will take P is on the boundary. So the coefficient becomes half. Then you find the missing data depending on Neumann or Dirichlet. Then second time I will take the P inside with the coefficient 1, solve the integral equation, and I keep on varying P. So I am taking P at any interior point, I can get the solution. Not like finite difference method. So that's the power of this boundary element method. Okay. So somebody maybe before 5 minutes raise their hand. Okay. So this is the setting of boundary integral method for only Laplacian. Okay.
Thank you.
So now how do you solve this? The idea is the boundary, the domain is irregular, so we cannot solve analytically. So you have to do some approximation for that, solving the integral equation. So how do you approximate? Suppose you go for a discretizing of the boundary, then these are the elements. Simple approximation, you say, I am going for constant elements. What do you mean by constant elements? Function as well as the derivative, both are constant throughout the element. Throughout the element. So then if it is linear element, so then this is the constant elements. Throughout it is constant, and you go for a representative node, which is the midpoint. So each element has a representative node, which is the midpoint. Since the value is constant throughout the element, I go for the midpoint as a representative. And linear elements, you need 2 endpoints. Then quadratic. Okay. So today I will show you the calculation with only constant element. Okay. So how do you have to, all that you have to do is you have to integrate this integral equation. That means you have to just evaluate this integral on the entire boundary, right? So we have discretized. So now you can see. So once we have discretized, so ith element, jth element. So each element has 2 endpoints. Okay, and this is the nodal point. Okay. So now, since it is constant, integral gamma is discretized into, say you are discretizing into 100 elements. So what will happen to integral gamma? It will be sigma gamma j from 1 to 100. And on each gamma j, phi and dou phi are constants. So they will come out of the integral. So you will be left with solving these. Just that you have to solve these coefficients. Okay. Why these coefficients are coming? Sorry. These coefficients, integral derivative of the Green's function, integral Green's function. And this psi will come out, dou psi will come out of each gamma j. Okay. So our differential equation is reduced to integral equation. Integral equation is reduced to solving local integrals of each gamma j. And what kind of integrals they are? Singular integrals. Why? Green's function is ln r. Derivative of that is 1 over r. So it's more singular than ln r. So you will be solving weakly singular integral, strongly singular integrals. Okay. So how do we solve? We use the standard Gaussian quadrature. So use the standard Gaussian quadrature and solve these integrals. Okay. So with that, you can see, so we have taken 16 elements for which analytical solution is available. Okay. So you can see a nice comparison. This can be done for any irregular geometry as well. Okay. So this is just the motivation of the boundary integral method. So for example, d is the distance and h1 is the height. So naturally, it depends on the both. So you have a trade-off between h and then you want to suppress, then you have one block there. So then at some distance, another block, right? So we want to understand. So simple model is you go for irrotational flow with water, right? So incompressible, then irrotational, so that you have a velocity potential. So then you are talking about the wave. An incident wave is coming, then it is hitting the structure. So then how much energy it is reflected, how much energy is dissipated. So we want to understand. Okay. So this is the typical model, and then you play with the different structures. So this problem, otherwise solving using the finite element method, etc., is quite computationally involved. Not only that, suppose you have a small thin barrier, and most of the barriers are not very rigid. Why? If it is very rigid, because of the wave hitting, it will be broken immediately. So instead of that, they will go for slightly permeable, so that some energy is passing through the structure. Okay. So you can see some beaches, you can see lot of small gravel is packed, right? So why gravel? Why not a concrete full cement? This thing, it will be gone very soon. Okay. So the energy has to be absorbed by the packing. Simultaneously, it has to reflect. So such thin barriers are often they are permeable barriers. So solving Laplace equation with such a thin barrier, you have to fit boundary condition this side, fit boundary condition this side. So traditional methods, they are difficult, and then how to handle the corner singularities. So there are a lot of issues, right? So what is the physics of the problem? Suppose you have a barrier here. So left potential is 5 plus, right potential is 5 minus, and you solve Laplace equation rest of the domain, and you have a free surface condition here, and a bottom boundary condition here, and try to solve, right? So it depends on what is physics happening at the interface. So since it is a slightly thin permeable, so there is a jump in the flux. It's not that flux is continuous, there is a jump in the flux which depends on the permeability parameter, etc. And then using Bernoulli condition, you get the pressure jump also. Okay. So now this has to be solved as a multi-domain problem. Why? See, you have a thin barrier. So now as a multi-domain, you create fictitious boundaries. Then this is R1 and R2. So then solve this problem and solve this problem, and then so it's a heavy duty computational. So in this boundary integral method, so we can handle this as it is by fitting conditions as it are here. So some convergence analysis we have shown. So let me show you the test cases. Two barriers are thin plate barriers with a distance. This is case A. Case B is L-shaped, repulsing. Then case C is inverted T-shaped barriers. Case B is L-shaped, facing each other. So with these barriers, we want to understand when do you have optimal dissipation of the energy, so that the structure is not damaged and the flux is not spilling over, so it will stop the wave energy. So that's the optimal configuration we want to estimate. So for these barriers, if you see, C is inverted T, okay. So up to some threshold normalized KCA, for example, so maybe I don't see the color. Okay, this is KCA. But if you see KC, up to here, it is in the second position, but after threshold, so the transmission is minimized. For the KC configuration, the transmission is minimum. Out of these 4 configurations, this configuration is turned out to be when beyond this threshold. Suppose you are having this K0H within this range, normalized, then definitely this configuration is not optimal. You can go for this one. So either you can go for B, so this one, or you can go for D, so this one. Okay. So this gives an idea of what, depending on the physical conditions, what trade-off you have. Okay. So this is the transmission and this is the reflection. So this will show the maximum reflection happening for this configuration. So once you have this behaves opposite. Okay. So this is an experiment which you can do with the different configurations, etc. So based on some existing cases, we have taken some configurations to match it, but otherwise, this is a new configuration, inverted T, and you get the optimal. Okay. So those who are interested, so they can see the details here. So then the second, so the highlights already I discussed now, the trade-off between the height and the distance. Okay, you can. So the second application I want to discuss about fluid flow problems. So in viscid flow, we have discussed rotational in viscid flow, just Laplacian. But now we are increasing the complexity, so we are talking about viscous flow. So typical Navier-Stokes equation, linear inversion. So you have viscous forces and pressure forces. So then if you are adding some particles to the free flow, you will get an additional resistance, damping down, which depends on the spacing of these particles. Okay. So now these are vector equations, whereas the Laplacian is a scalar equation. So these are vector equations. So how do you, these are primitive variables. If you want to solve the problem in velocity and pressure, primitive variables. But what we do, we switch to scalar. 5 minutes. Okay. So what we do, using this equation of continuity, we can introduce a string function. Why? Dou E by dou x plus dou E by dou y is 0. So I can plug in a u there and v there like this with the exchange of derivatives with the negative sign. This is identically satisfied. This is called a Stokes string function. So then if you substitute this in this and eliminate pressure, you get a higher order modified Helmholtz combination. So here you are getting Laplacian and modified Helmholtz combination. You can introduce a vorticity, then you get a coupled Poisson and modified. So you have a Poisson equation, you have that. It's a one-way coupled, where omega is called vorticity, psi is called string function. So now, since the operators are linear, I have a Green's function for the Helmholtz equation. We develop a coupled boundary integral method. So this is the coupled boundary integral method. So the numerical solution of it, similar to whatever I have shown, with constant elements, you can discretize. So using this, we want to discuss an application of carbon capture. See, for example, this is an analytical work which we did. So nowadays carbon is not thrown into the atmosphere; it is captured underground. If it is a straight channel, so there is a possibility of leakage. But if you go for wavy channels, there are circulations, so the carbon is captured and you have immunity is disturbed. So this model we have implemented using coupled boundary integral method, and we have estimated the boundary thickness and error convergence. So those are interested, they can see. This might be a student who is at IIT now. So those are interested to learn boundary integral method. This book, this is a very good book. PDF is available. Okay, and this is also some maximum 73. So once again, thanks to the organizers. Any questions? I'll be happy to.
We thank the speaker for excellent presentation. Any questions?
Yes.
So the solution in the interior will be almost equivalent to the continuous solution or AMSE solution.
Now this technique advantage.
Yes.
Except the boundary.
Yeah. So can we talk about the speed of convergence and what are the factors that can accelerate the speed of the convergence? Means how fast it converges to the thank you.
Compared to gradient, you have only Gaussian quadrature and one. That's all. See, the boundary integrals are solved using Gaussian quadrature. So now it depends on the number of Gauss points you take, the convergence and error contributes only to the display. Okay, so for example, the L2 error that I have shown is quite close to the real solution. For square domain, I have the analytical solution. When I compare, it's giving almost accurate. Okay, but for these irregular domains, the L2 error is pretty good, close to 10 power minus 6.
It also depends on the number of points.
But I am not saying this has a rate of convergence because this is it's only boundary display. So there is a concept of rate of convergence. I can measure the error in the solution, right? Because rate means I am only doing Gaussian quadrature.
It's the overall error.
Overall error or the local solution I can come to. So how do I come to? Suppose I have a Dirichlet diagram. So then what do? I come to the missing data, Neumann diagram. So now why do I check it? I plug in the Neumann diagram and then retrieve the original Dirichlet diagram. So then there will be a noise. So that will be estimated. That much I can.
Any other question? Question?
Problems.
Yeah.
Linearized,
So for a nonlinear problem or even simple Poisson equation. So for Poisson equation, if I try to do it, what will happen? One domain term will be thrown on the right hand side. But I can still reduce the domain integral to boundary integral for Poisson. But once it is a nonlinear, let us take del square u plus u square equal to 0. So then your domain term integral will be Newtonian potential integral u square product with the Green's function will be floating. So principal part is Laplacian. I will use Green's function of Laplacian, still manage the boundary integral, but this term will be floating. So Newtonian potential you have to go for domain. So you cannot escape. So you have to go for both combined boundary plus. So that's it.
Any question?
Yes, sir.
So, sir, if the function is not Green's type, so can you apply this?
No. I need it's a standard algorithm. I need Green's second identity. I need Green's function. Then only boundary integral is derived in terms of the Green's function. There is no other method. So what do you mean by that? I am distributing the singularities of the linear operator on the boundary with an unknown density. And what is the unknown density? Function, derivative of the function. So they are the single layer potential and double layer potentials. So your solution, you are distributing in terms of the
So if the
single
boundary,
solution.
if the boundary is a Robin type of boundary, then can you apply?
Oh yes. So Robin type also I can, then I will not get a straight boundary integral equation. I have shown you first boundary integral with the function, then derivative of that, so then it will be a combination of it. You can handle it. You can handle it.
Yeah, the question I would like to ask is similar to you have answered already. When you have all the problem, you have to deal with the boundary and the domain of the problem. For example, in Navier-Stokes equation, you always have for highly nonlinear problem. You can deal with the boundary, imposed boundary condition, and use boundary elements if it's regular boundary to have very adequate results. But the domain of the whole thing, when you talk of channel flow with regular like blood flow, where you are putting the non-linearity into the whole thing, the convective terms and all those things, and then you have to combine the two. So thank you very much for excellent talk. Let us thank you.
Thanks to the chairman.
Thank you, Sir. Now I will request Professor Ajay Kumar Mahapatra to please felicitate him with the moment.
Yeah, please. So thank you very much. My pleasure for thanks.
Thank you, Professor. Our next speaker is Professor Nadesan Srinivasan. He is in Department of Mathematics, IIT Guwahati. His research interests are numerical solution of differential equations, singular perturbation problems, homogenization, multi-scale problems, big data analytics, and computational finance. He is also the editorial board member of International Journal of Mathematical Modeling and Numerical Optimization, in the science publisher, Geneva, Switzerland, Computational and Mathematical Methods, Journal of Applied Mathematics, and many more. With this, I request him to present his talk.
Thanks to the organizers. Good afternoon, good morning, good afternoon. Thanks to the organizer, particularly to Apple for contacting me for 8 or 10 months before for the conference. In fact, she wanted on the first day because of our registration and new semester, we are not able to. So, with this, you will let me start. The topic, this is more on the side of we are trying to solve, and then you study some error estimates and all. So here you can see the title. It says that this is the time fraction between liquid last one decade. So we are able to encounter many on the application of the fractional differential equations. Both are there, time as well as the space fractional. So here in today's talk we are focusing on the time fractional. And then to solve this, so it's a two-dimensional problem. So we wanted to try to, we know that even in the normal sense, if you want to solve the two-dimensional problem, so we are able to have, suppose even the integer order derivative, suppose if I take ut minus Laplacian u, then we know if we discretize that as it is by some backward Euler or maybe Crank-Nicholson, the matrix which we will try to encounter is going to be of the pentadiagonal with the high bandwidth. It will be difficult to solve that system. So the ADA type of methods came into existence, where we will try to use first x-axis may be an implicit and y will be explicit and vice versa. And there are some fractional order methods and all, but here we are using another type of method where we will try to split that into two operators, that is x and y direction. Then we will be able to solve. And the resultant problem is solved by using finite element, and that is discontinuous Galerkin DG. And this is one type of DG, that is non-interior penalty Galerkin method. So this is the title, so which we are trying to solve. So this is just the outline. We will able to see as much as time permits. We will try to see. So this is just a history to give the fractional calculus. When it started and all, this is as old as the integer order calculus, but due to some reason it didn't come into light. Okay, so you can try to see the various applications. So this is also, when we are talking about UT, you know that order will be the first order and all. So if I want to try to take what will be the, suppose that alpha, let us say parameter, which lies between 0 to 1, the unit interval. And if I want to vary that alpha, what will be the limiting case and what, how the derivative will be represented mathematically. So since the order lies between 0 to 1 or 1 to 2, the subdivision or superdiffusion, we can try to see the derivatives are in sense. Okay, so started from Riemann-Liouville, there are some drawbacks which are overcome in the capital sense, and there is and so many other still going on the long list. The generalized one, there are so many generalizations, that is the problem here. Okay, so we will able to see lot of equations of that type. So again, we try to see the another important application for the time fractional. Basically here, the memory effect will be taken into consideration. Okay, so which will not be available in the case of the integer order. Okay, so we can see this example. So the governing equation of the evolution of this PDF of the non-Markovian process. So that we can try to consider as a time fractional equation. Okay. So this is of course some preliminary just to give you how to define the integral first, then the derivative. Here also I can try to define the left and right integrals of the Riemann-Liouville sense. So you can see here where it involves the gamma function. So I will be able to define between a to t this one. Similarly for the right. So using these integrals, now we can try to define the derivatives. Okay. The derivative of those integrals. Okay, so this is the Riemann-Liouville RL. If you go to the capital, that will be the other sense. The derivative, integral of the derivative. So here, the derivative of the integral, so there, that is vice versa. Okay, so here we are able to see. Again, the gamma function shifts, but whereas that this is the derivative. So here, of course, the existence of the derivative is required, but whereas here, the previous case, that is not required. Okay, so that is the only one difference. When we are see between the, of course, we can connect both, and there are a lot of properties and all. We will, because we have less time. So when we go to study the numerical aspects, that is that error analysis and all, we try to encounter the Taylor's expansion, whether whatever you do, either finite element or difference or anything. So in order to make the generalized presence, so we need this new function called this entangled function. Okay. For the one parameter, we can define the k. You can see here the k summation runs from k 0 to infinity, and this beta is the one parameter which we are going to consider. Okay, we will have the generalized sense of the exponential. Okay, this is your exponential x only, but the generalized sense. When we are having two parameters, of course I will be able to make. If I try to take beta equal to 1, I will get back the exponential function. If I try to take beta, gamma, for example, here gamma equal to 1, I will get back one parameter 1. And if you try to take, both will be equal to 1, I will get back exponential. This is just the basics to start with. There are a lot of physical applications. I will give this all in the generalized sense. Integer order we know, the geometrically. If you will try to take the integral of A, the area, so here that is going to be the generalized sense. Okay. So geometrically, physically we know the rate of change, the displacement. So here is the generalized sense. Again, both the derivative, whatever we will try to call, either the RL, that is the Riemann-Liouville, or the capital. Both we can try to take. Okay, so this is the general idea of the physical interpretation. So if we try to consider this is a monotonically increasing function, so y1. So then this will, we know that is the slope, the general derivative, but here the generalized sense. Because of that will be in the terms of the integral. Okay, so with this introduction, just we will go to the model problem which we are going to try to focus to solve numerically. Okay, so this is your, the special derivative where we are having the Laplacian and the convective term, and then we have the zero product term. Okay, all the coefficients or all functions of both the space as well as time. And we can see here instead of ut, we are having the capital type fractional order derivative. Okay, so if you want to solve this as it is without exploring any of the operators within or 88 type of scheme, so corresponding to this we will get an integral term. Okay, so then the discretization, this will remain the same as like the special derivative which we will try to do for the integer order, and the bandwidth of the matrix will become too large. Okay, in order to avoid that, the computational cost, we try to use this operator. Okay, so here we make some assumptions on the coefficients because we want to provide the error estimates. Okay, since we are using the finite element, so we need all these assumptions in order to ensure the existence of the weak solution and all those stuff. These are routine things. So what we will do, we try to split this operator L in the x and y directions. Okay, so that is what we are doing here. I will call this is Lx corresponding to the x direction. Similarly for the y, we will have the Ly. Then I can rewrite that model equation into this form. Okay. So now this is that one. So for that, of course, these assumptions what we are taking, that is required. Otherwise, you won't be able to make it. So now we can see here what this figure represents. So this is, we try to proceed that sweeping in either the x direction first or later in the y direction or vice versa, we will be able to make it. Okay, either top to bottom or bottom to top. Okay, we try to make in that way the operator splitting which we have done just before the work. So now, the idea is what we will do, we try to introduce an artificial time step. Suppose if I want to solve the interval Tn to Tn plus 1, at Tn plus half, I will be able to make an artificial step. Tn to Tn plus half will go implicit in one direction, explicit in another, and vice versa will go in the rest. But here, we are not doing that. Here we are trying to take same domain, omega across Tn to Tn plus 1. And the first sub-problem, which we call the x direction, we will try to calculate that V star with the given initial condition. And for the rest of the problem, the second one, we try to use this solution V star and the initial one. That means we solve and some sort of upgradation we will try to give in the rest of the problem. Okay? So that will be the idea which we are trying to make it over here. Okay, so that is what the operator thing does. Okay. Now you can see here, in principle, all the fractional order derivatives will have singularity at t is equal to 0. Okay. So one has to use some non-uniform green. Okay. But for this study to start with, we try to take the uniform green just to understand how that will work, and then to discretize the capital derivative because of the integral sign, because this is the integral of the derivative. So first I replace the derivative by some finite difference quotients, then I will try to approximate the integral. So here we try to use the trapezoidal to integrate that one. Then we got this formula, which is the L1 which is first order. There are higher order things exist, L2, L1 sigma and negative. So now we can ask what will be the error after discretizing the continuous derivative by the finite this difference. Then we will be able to obtain the order will be constant times tau raised to with the step size. What we are using delta t basically 2 raised to 2 minus all of the raised. So now we can use some higher order scheme because the special derivatives we are going to use the second order. Obtaining overall second order, we are using here the L2 scheme. So here of course this is quadratic interpolation. So I need one more step in between. Okay, so that is the main thing. So I need 3 points to solve that integrate. So okay, I have approximated that at k minus t, k minus 1, tk and tk plus 1. So only a starting point we will have some difficulties. The later we will be able to overcome this. Okay, so then we will have to obtain the second order approximate solutions. Okay, so these are all some derivative. So we skip here. So now it's a second order one. So I will be able to see here the discretization, the error from the capital derivative will be of order 3 minus alpha. Since alpha is between 0 to 1, so this will be of the second order. So here, the main thing one has to note. So, okay, so we require 3 points to discretize the derivative, that is using the L2 scheme. So, if you want to get overall second order, I have to use the L1 scheme with this order, the time step. Then overall we will be able to retain the order. Otherwise, the order will get diminished. Okay, this is one thing. When you want to go for the L2 type, okay, one has to remember. Okay, so that is the one constraint because we are using this at the 3 points. Because the start is like multi-step scheme. When we are solving the first order ODE, so it's not self-starting. So I have to go up to that point. From there we can pick up that. The same idea over here to make. Okay. Now this special discretization. So for that, one can reduce the continuous galaxy. So, but in practice, there are a lot of physical problems where the solutions have interfaces, discontinuities across the domain or across the boundaries. Suppose the material, if you take two different kind of material, then the physical properties. In those cases, the DG type methods will work well, and it is very easy to implement also. You can try to see there are a lot of literature over here. There is one of the good book, one can try to understand how the DG things come into existence. Okay. So now, here there are various types of methods. So we are going to pick up only one, that is symmetric, irregularity, non-symmetric, and IIT, many methods. So here we are trying to take one of the specific one, that is NIT. Okay. So we try to discretize the domain. So this is on the x and y direction. So these are the elements. Okay. Then for the whole domain, the tensor product of these grids will give you the discretization. Now for the boundaries, we will be able to have the discretization. Now, because of this DG, across the boundary elements, there will be a discretization. Okay. So we have to define the jump, and we have to define the average in order to estimate. Okay. So we will come back to the standard Sobolev space where the functions are all L2 and the gradients also restriction to each element will have to shown over. Okay. So this is for the boundary where we are able to isolate a boundary condition. So now for both x and y, because we are going to estimate the error for the problem 1 and 2, we require these two spaces. Okay. Now we can define the norm and all those as usual. So now this is the polynomial space. The polynomials of degree are its direction on each of the elements we will be able to make. And you can see the restriction. So they are going to be on. Okay. They are L2, whereas across the boundary there may be a discrepancy. So that is the idea of using this. Okay. So we will be able to define the boundary value where this is a subspace. We are trying to define the subspace. Where S stands for delta x, that is special discretization, R stands for the polynomial degree. Similarly, for y we can define, as I pointed out, there is discrepancy across the left and right limit. So I can have a jump, I can define the jump and then the average. Okay, so this is the jump. The difference between the right and left limit, this is the average. So which will be required in the bilinear forms. Okay, so now I can use the fully discrete scheme, which consists of the L2 for the time derivative and then the NIPG for the spatial derivative. So for subproblem 1, I am having this, subproblem 2. Now for Lx and Ly, we will be able to have this. So I will have this bilinear form. Okay, Ax corresponding to x and Ay corresponding to y, which are defined over here. Okay, so you can see here. So we will be able to have all. And you can see over here, so we are having the average and then we are having the jump. And this sigma I1 or the penalty parameter. Okay. I can try to take different parameters, depends on the nature of the problem. Okay. Similarly here, I have sigma j of, this is the x in y direction. And then we are having the jump and average, the rest. So these are the extra terms. If you try to make the continuous Galerkin, many of those terms are going to disappear. It will not come into the picture. Now, to estimate the error, we are going to define the energy now, that is the discrete DG energy now, we are able to see. So this is corresponding to the penalty parameter. Okay. Then we can prove the coercivity of those operators, the linear form, AX and AY. And now we can have the stability estimate. Okay, still goes. Proof, I think I will skip because we have less time and more mathematical involvement. So now I can able to give you the error estimates which we are going to try to see in the solutions of subproblem 1 and subproblem 2. Okay, the stability estimate we are able to give for both those problems. Okay. So you can see here the stability estimate depends on the initial value plus the source function which we are going to have the original problem. Yeah. So now once we discretize all the problem and all, one can ask how well the solution is approximated. That means whether we will be able to determine the error, okay, mathematically. So when we are having the error, there are two things. One we can call this a priori error, that is before calculation. The another one is a posteriori error, after the calculation, which is a calculatable bound. So in this study, we focus only on the a priori estimates. Okay. So we try to discretize the error into two parts. For the problem 1 and the problem 2, and that will lead to another two parts, one corresponding to the projection error, and another one is the interpolation. Okay. Generally, when we make the finite element, the discretization error, then the interpolation error. Okay. So here, that will be done using this projection error, Px and Py. So now, we can try to see the error corresponding to the projection. We will have the C into H raised to R plus 1. Or is the polynomial degree, okay, which we are going to calculate on these two subdomains. Now, for the discretization error, I will be able to give you, so this is you can see here. Yes, these two parts. The discretization and then the projection error. So, the projection error is this, discretization I will be able to give you. That is H raised to R plus 1 the same order what we got here, plus the L2 scheme corresponding to the capital discretization. So now, this is again the proof of the here one. So I will skip. So we will be able to obtain the final estimate, which will be the order. So if you want overall second order, so that way we are using this R equal to 1 for this linear polynomial. I will be able to obtain the overall second order estimate. Okay. So now we can do the error of this fully discrete scheme. So we will create this for both subproblem 1 and subproblem 2, because we already splitted that operator in two parts. So now let us take one model problem. So where we implement the study of the method. So we are going to take this capital derivative minus Laplace u equal to f. And we are going to take the exact solution, the smooth function here. So if you want to take some non-smooth, because we are using the uniform grade, but in reality there is a singularity at time t is equal to 0. So accordingly I can choose an exact solution, then I calculate the right-hand side. This is the initial and these are the boundary values. Okay. Now we will try to estimate the error. So on L2 norm as well as on the energy maximum norms and the order. The sequence, of course, what order it converges, it can be calculated using the rate. So now, this is a solution. For example, if you try to see the alpha, which is between 0 to 1. So here we have taken alpha equal to 0.4, and we have tried to take 40 number of subdivisions in all the directions, delta x, delta y as well as delta t. And the final type is equal to 1. There will be the exact and then the calculated solutions. Yeah. And you can try to see here. So the error between both, there will see that is raised to -3 what we got between both these numbers. And this table displays the order, the theoretical one, just to validate those estimates. So you can see here as alpha starts from 0.22, it's raised between 0 to 1. So starting from, we can calculate all, but we are given only few selected values. Starting from 0.2 to 0.8. You can try to see the order, the theoretical order. If you try to see here, so this is the, yes, this is going to be the, okay, tau raised to 3 minus alpha plus h raised to r plus 1. R equal to 1, that is polynomial of degree 1. So h is equal to 2. And depends on that alpha, that order will change. Okay. Overall, we will obtain the second order estimate. Okay. So r equal to 1. So here, in order to show the time effect, we are trying to take the, you can see here, which what we got is tau raised to 3 minus alpha. So I have to try to take tau minus 3 by tau minus alpha over 2, then we will able to obtain the overall 2. Okay, that depends on this order of your delta t. Okay, you can see here, as long as this alpha is small, we are going to be close to 3. Once alpha goes closer to the right hand side 1, that is going to become, okay, 3 minus alpha over 2. So just to conclude or summarize, so in this talk we have taken the time Laplace, the time fractional of the capitosens, the two-dimensional PDE subdivision equation, because the alpha is between 0 to 1. We can take the super division also 1 to 2, then the study will be different. And to reduce the complexity of the computation and the analysis, we have made the operator splitting. Here the original operator has got into 2. One is on the x, another is on the y direction. Then we try to estimate the error to solve the splitted problem. We have tried to use the L2 scheme for the capital derivative, and then NIPG, a non-interior penalty, the Gallatin method to solve the special derivative. Then we obtain the required error estimates, and that has been validated to that exam. Okay, so we already derived the estimates. So there are a lot of things can be done in this direction. So suppose if we try to take the two-dimensional Bulgarian equation, okay, which is already quasi-linear, and you want to solve, yes, we can try to use that we are trying to work. Because of the non-linearity, the expected order of convergence is not gaining. Then there are some references. These are all from the NAPG to C. And yeah, these are all from the great work. This is the joint working Sandeep. On the faculty over SR Chennai. This is not a good book for this DG. Yeah. Now these. Yes.
Sir, what will happen? Consider alpha becomes variable.
Huh?
Alpha becomes variable.
Very good. Yes, we have done that also. If alpha depends a function of t.
Yes.
Yes, we have done that also. But there the analysis will be more complicated. Yes. We have done as alpha, the generalized.
Alpha must become from 0 to 1. Now we have to consider the function like that.
Exactly. Yes. We have done with Anil Udo, another one. Yes. Generalized memory kernel. We have done that. Yes.
Can you get exact solution at that case?
Maybe for the high problem we can make, or from the exact solution we can calculate the right hand side. That's why this numerical analysis. We have taken the high problem just to implement to show how that will be. But when you go to the practical cases where we don't have the exact solution, we can trust to that. This is mathematically proved. Addition to that, we have validated the theory. That you can derive on the general system. That is not possible. Even in this case also, it's not possible to get the analytical solution. It's very difficult. Even the linear problem. And that is there, the generalized memory kernel. You can do that, that also belongs to a function of D. Yes.
Yeah. Any other question? Yeah, okay.
Thank you, sir, for the nice presentation. You have used some periodic terms during the
Yes.
So, there, I want to know about the choices of the periodic parameters that you very sequence.
Yes. So,
Is there any optimal choice so that
Yeah.
Yes.
That depends, I already told that depends on the nature of the problem. Suppose we have put material, suppose the discontinuities, then depends on the smoothness of the solution, one can try to choose those parameters. As far as this type problem is concerned, the solution is smooth, we have tried to take them, that should be, you have tried to take anything 0.5 or 0.6, whatever you take, it doesn't matter. Both you can take the same or each element you can try to take. That is, depends on the physics of the problem. That way, it is, you can choose. Yes, exactly, yes. Otherwise, that the bilinear form what we saw, that may not be question.
Yes, okay.
Sir, in error calculus, so we are counting two types of error. One is the discretization error, another is the approximation error.
Yes.
So among these two, which one gives more contribution error for a discretization? Have you compared it?
No, error is the one. For our
No,
convenience,
overall error is-
we are dividing that into two parts. If you do many difference, then we have only the discretization error. That is Taylor's expansion, easily you will get it. But here is a finite element, so we are having the integral. There are two errors corresponding to that, because the derivatives are going to be under the integral. So we are going to have, that is the projection error we calculate. Discretization one, whatever we do in the finite differences. Both are equally important.
Both are equally.
Yes. Otherwise, overall we are going to get na. So that for our convenience, we are divided into two components. One is corresponding to the projection or the interpolation, and the other one is corresponding to the stress. Both.
Yeah, okay, sorry.
You have used, because we know that there are Fishman and Poole on numbers approach with two techniques. In general sense, we calculate at an imaginary point Tn plus half. But here you have said it is T star.
Yes.
So is it arbitrarily chosen, the T star?
V star is nothing. So here V star, what we have done, we are solving both the problems in the original domain. We are not having any, if you see the omega cross T to Tn plus 1. So there is no other way, we are having the time stepping, either in the x direction first and then the y direction. The second problem, initial condition, will come to the first problem. We solve it, some sort of upgrading the solution. I will solve it first, then I will update the other. So that is it.
Yeah, it seems you have a lot of questions for
In the temporal direction, you are using advanced student, you are getting 2 minus half. And when you are using active scheme, you are getting 3 minus half.
Yes.
So is there any higher order scheme in temporal direction?
That's Siksha, no. This is itself very difficult to implement. Okay, practically we can go, okay, theoretically I can talk, but even the estimating, those things are not easy. Okay, so this is the maximum as of now. But you have already seen, even to get that also, I have to use the quadratic interpolation. Look like a multi-step scheme. I have to evaluate that, the L1 scheme with certain order in order to get overall that estimate. So if I take more, I think it will look like a multi-step scheme. Okay, beyond certain order it doesn't have. Okay, in bit less if you want, you can have this L2 1 sigma. L2 1 sigma. That is just the order name L2 higher order than L1. But as of now, this is estimating the theoretical part also very difficult.
Okay, the question I would like to ask is,
Yes. Yes.
in terms of numerical analysis and the techniques of solving problems involving time fractional derivatives, model problems, I think, I mean, for 2D problems, it's extremely done well. My major problem in many things I've seen there is the aspect of the model itself. When applying it to model, to physical problems, there is a major problem that arises from the living, which people are not realizing. You see, you know, the EAT equations which you display the solution is well known. Without alpha, when alpha is 1, we can tackle it and solve it with any method, finite element, finite difference, get nice result and so on. And EAT equation is a physical problem, which we all know. All the variables there have dimension. Time is in seconds. The U or whatever is temperature in Celsius or Kelvin. Now, when you look at the diffusion part, you see, when you look at that, by the time you introduce alpha into the whole thing, it destroys the EAT equation. Because you must model the problem to make sure that the dimension are balanced on both sides. But people put that, they still call it EAT equation. It's not more EAT equation. It doesn't represent anything physically. So, but the solution is there. Because when you look at that model, you only have alpha in the derivative, time derivative. On the division part, you don't have the depth squared and all those things. Now, there is no alpha, there is nothing, the unit is not balanced on both sides, so it doesn't represent any physical problem. So, my question is that mathematically is a solution, but physically, does the model represent physical problem of each, we call it? So we need to take note when we are using fractional derivative to physical problem, to make sure that we balance the unit dimension on both sides. Because when you look at the analysis of dimension on both sides, you are now having seconds raised to power alpha. And you look at the right side, the division. Y is in meter, and this is Celsius. So you can see the diffusivity that is there, which is on the other side, maybe it's meter square per second. That does not balance. And at the end of the day, we are not solving real life problems. We are just putting mathematical solutions to problems which has no applications. I told that Tangana that realize it. I told many people when I travel, when I use fractional calculus as well, and people are just putting alpha in time and it's not like that. If you apply it to Navier-Stokes, you must remodel your Navier-Stokes to make sure the units are balanced, because we are not having fractional time. And you must balance it with all other parameters variables that are there to make sure that when you check the parameter and the balance of both sides, then you are solving Navier-Stokes with fractional derivative. So these are the areas that have disqualified many things. Where we say, okay, this is not balanced. Yes, it's a good solution, but it doesn't represent anything. So let us be careful in the physics of the problem before we apply our mathematical method. It's a good method, fractional calculus. Very good method. But if we are just doing numerical experiment, it's good. But we are now applying to real life problem. Be careful to make sure that your model is physically realistic before you start. Thank you very much. Thank you for
Here we are having the states derived fractional as well.
Yeah.
The Laplacian also we can define in terms of the fractional derivative.
What I'm saying is that you look at the example. You go to the example there, you will see what I'm saying. You only have for the time derivative that is fractional. On the division part.
That is the subdivision.
Yeah.
The subdiffusion.
Subdiffusion.
Yes.
It's not fractional.
Yes.
And now, if you look at the dimension of you call it EAT equation. You look at the dimension, it's not balanced. Because for those who are doing mathematical modeling, you know that T you have there, it has a dimension of second. EAT equation already, du dt equals to alpha grad square u dt dy squared. It balanced, mathematically balanced. You can derive it from first principle. If you add them, you can get everything right with all the parameters. But when you introduce alpha to the derivative of time on the left side, and you are now applying fractional derivative, look at the unit on both sides. The dimension of both sides does not balance anymore. It's no more EAT equation, it's something else, which you don't know. So which means you can't derive it from first principle. But there are ways of doing it to make it balance. For mathematical, numerical experiments, good. But for application, it doesn't apply to it, except you remodel it on the right side, you check the dimension. There are things you have one have to do to incorporate on the left side or right side and so on to make sure the dimension are balanced. Then we can now continue with our fractional derivative. That's what I'm trying to comment. Because I've seen many people like that, and when we talk, we check, and they say, oh, it is true. Because you want to work either in dimensionless or in dimension. When you work in dimensionless, one is having dimension, the other is one dimension. What do you do? Is that both of them have equal dimension or they are all dimensionless? So I'm talking, I don't know whether you are a numerical analyst, but for those who are doing mathematical modeling and physics and so on, you understand what I'm talking about. So sorry for that. Thank you very much for the excellent talk. Thank you very much.
Thank you so much, sir. I would request Professor Satyaranjan Mishra to please felicitate. Thank you so much, sir. Our next speaker is Professor Samarjeet Garg. He is currently a professor in the Department of Mathematics, NIT Durgapur. He is also an active participant in Chinese academia, having served as a visiting professor at Tsinghua University and as a co-investigator of two sponsored projects funded by Natural Science Foundation of China at Tsinghua University and Nankai University. He has delivered more than 20 invited talks at various Chinese institutions. His current research interests include operational research and optimization, software, machine learning and uncertainty modeling. With this, I request him to please begin with his talk.
Good afternoon, friends. First of all, my sincere thanks to the organizers for giving me this opportunity. So I'm really very happy to be here today. And this is my second visit. I think 10 years back I came here for attending one international conference by Operational Research Society of India in 2015. Anyway, today's topic is optimization and machine learning. So this is the outline of my presentation. So first, why optimization is involved in machine learning and for different mathematical formulation of different mathematical models, how optimization works. There are several machine learning techniques like supervised, semi-supervised, unsupervised, and reinforcement learning. How mathematical you frame those and how optimization works there. And there are different optimization tools people have used nowadays for machine learning models like gradient descent, stochastic gradient descent, and others. We will give some few of that. So conceptually how any mathematical, any machine learning problem, how we design mathematically. So there are several stages. So obviously, in the first stage, obviously we collect the data. This data in different form, it may be image data, maybe real data sets, or any video data. Different types of data are there. Maybe photographic image, or maybe stock price from BSc and so on. So obviously the first stage should be pre-processing. So for pre-processing, obviously if we consider the image, so image of a cat or image of a dog, so obviously only one face of image is considered, like face is in the center, so different parameters should be there. So how we can process the data as per different features. So next step should be the feature extraction, because there are so many features, but not all features are very important. So obviously the optimum number of features is also important. So how to reduce the raw data with respect to those features. Next is generation of training data. So that means from those data sets, how actually we split this training and testing data set. So there are different samples may be considered for the training purpose. So how we generate those data? The data may be in the form is xj, yj, where xj is the feature vector, that means the level or output maybe depends on several features, maybe individual vector, and yj is the level vector. So the next step is very important. So because by training we can determine the corresponding feature value and how it is actually different from the exact feature value. So that means we have to design a loss function. So obviously for that loss function may be in different types. It may be this form, or maybe in different form also. So then other two steps are also very important. First we have to learn the model. That means learn the model using those training data samples. And then obviously characterize the general error, because that maybe the training error is less, but it may differ from the test error. So only the generalization of error is important. So how to build the selected model on the mean data. So obviously most of the ML basically boils down to optimization problem. And optimization is in different forms. Sometimes it may be in different machine learning models can be considered as a black box system. So that means obviously it is much more faster nowadays. But how actually optimization plays an important role, that is very important. So obviously for those parameters, they are giving the different ML parameters. So how actually we optimize those error terms or loss terms? So if the function is convex, obviously, or maybe in one dimension, it looks like very easy, but there are several directions or several features. So it's not sure. So obviously for any machine learning model, so there is a function that is optimization function, or sometimes it is called cost function, to optimize the performance measure of the corresponding model. So in pure optimization, obviously it's a goal how to minimize or maximize those functions. But in the case of machine learning, so we minimize this function A with respect to this model parameter theta on the training data set, so that we can minimize the training loss or training error. So obviously the test error or generalization error is very important. So how actually it is, how this test error is, whether it is similar to the training error or it is more, so that is the most important issue. So obviously there are basic assumption for this any machine learning model is test and training data are generated by a probability distribution process, because we are always considering some sample from the training data set. So obviously the data, sometimes this data is generated from the probabilistic fashion, maybe in online fashion or some other way. So this data sampling, obviously always this data sampling means data is always independent. So training set and test sets are identically distributed. That means always we should consider the sample from the same data sets as the training data and testing data. And finally, the performance of the ML is to ability to their training error is small in general. So then reduce the gap between the training error and test error. That is the main target. So obviously then the concepts of underfitting and overfitting of any machine learning model. So sometimes the model is not able to obtain sufficient low training error. So in general, theoretical concept, the training error may be 0. But sometimes the gap between the training error and test error is more. So in that case, the concept is overfitting is found. So pictorially, you just look. So for simple data set, if you consider, if we approximate those data sets by this type of highly nonlinear curve, obviously it satisfies all the data sets. So obviously here it is overfitting because the function is highly nonlinear, and in that case there is a chance of more testing. On the other hand, maybe training error is very less here. But on the other hand, if you consider simple linear function, so obviously here the variance is more, but the function is very simple. So that's why it is underfitting, that means here training error is more. So but if we design a quadratic function like this, so obviously it's a good balance between these overfitting and underfitting. So obviously this overfitting and underfitting is basically depends on this model bias variance trade-off. So from this figure, I think it is very clear. Just look, if your target is in the center point, and most of the data sets is close vicinities of that circle, so obviously it is low variance, both low variance and low bias. But on the other hand, if it is all the data sets in a small vicinity, but this is away from the target, so obviously here bias is more, but variance is low because they are close. But on the other hand, then here it is maybe they are to the center point, but they are scattered. So obviously here variance is high, on the other hand here both variance and bias is high. But theoretically we can represent bias as this expected value of this target value and the estimated value, and variance I think all of you know. But conceptually, if we consider this as a bias variance trade-off, so obviously with respect to the model complexity and error, if model complexity increases, obviously biases increases and variances decreases. So in that case, so that means there are basically a conflicting in nature. If we increase the bias, if the bias will increase, variance is less. On the other hand, if variance then bias is, so obviously there is a conflicting in nature. So this can be mathematically represented in this way. Suppose you have this is your function, and if you consider this epsilon as an expected value with mean 0 and variance sigma square, so then error function of x naught is determined in b square, that means expected value of y minus fx squared such that x equal to x naught. So this simple mathematically we explain it. This is, there are three terms, sigma squared by n, and this is the bias term, and this is the noise term. So obviously if n will increase, so variance is decreases, and if n increases, then bias is increasing. So that means variance is decreasing, but bias is increasing, so they are basically conflicting in nature. So how to control this? So obviously, conceptually, this bias variance trade-off is represented in this way. This is the model complexity and this is error. So that means if model complexity is increases, so that when bias is decreasing, then model complexity is decreasing, and when variance is increasing, then model complexity is increasing. So obviously, our target is to determine a good trade-off between these two bias and variance. Maybe this is the trade-off. So there are already I told you there are several models. So for simple supervised learning, when the data are level data. So in that case, obviously our goal is to determine this, minimize this loss function. So this is function of yi and fi x theta. So obviously for this loss function there are different mathematical way we can solve this type of loss function. So one of the important is regularization. So that means if we mathematically regularize this function by n naught, so this is represented by this way. Similarly, for unsupervised, semi-supervised learning, when some data are level, some are unlevel. So we can divide those level data and unlevel data into two ways. B is the level data and B is the unlevel data. So there is a very good method that is support vector machine. So where mathematically that support vector machine can design this semi-supervised learning technique. So here we minimize this function with some extra term, and there are some constraint. So obviously it's a constraint optimization function. So we may solve this constraint optimization function by different optimization techniques. Obviously there are some other models like unsupervised learning and reinforcement learning cases. So those also mathematically represented, because for unsupervised learning is basically we use different clustering technique. So in that clustering technique, we want to minimize the cluster distance, in distance as well as within the cluster and between the clusters. So obviously, always we try to minimize within the cluster and maximize between the clusters. So that may be represented in optimization form. Similarly for the reinforcement learning. So these are the different mathematical forms where we want to, because here the external agent works and always the external agent maximize the gain of that. So that's why this problem is represented as a maximization one. So all the supervised, unsupervised, semi-supervised, all are represented some mathematical optimization form. So now there are several optimization techniques. Some are first order method and some are second order higher order method. So some of my students work in this higher order method. So just I go through with some simple techniques by which we can optimize those machine learning models. So first of all, for the case of gradient based approach, so it's a very simple concept. So here, because if you consider a minimization problem, so obviously we should sequentially we consider this iteration is a several iterative way to find the optimal solution. So at first we initialize the weight vector, and then there are several iterations and determine the gradient. So obviously we set a learning rate here that is ITER, so which basically offers the direction of the gradient, because here we are trying to minimize in the object. So here the iteration rule is this Wt is Wt minus eta t is Gt. So where eta t is the learning rate. So obviously, if the function is convex, so obviously the gradient descent will converge to the global minimum. But in any surface, any higher dimension, maybe there are several local minima also. So it's obviously for the non-convex case, if we want to use the gradient-based approach, so good initialization is very important, as well as the learning rate. So this is the convex function. I think this is a simple function that form you can understand easily. This function is convex, so obviously this iterative process do very well, and we can get the global minimum. On the other hand, if there are some local minima, then it is really difficult to determine the corresponding global minimum. So obviously we will move in the direction of negative gradient, so in the gradient-based approach. So obviously if in this gradient-based approach, if we want to maximize the function, then also it's very similar, this iterative process. So only thing here we use this plus term. But one more thing, so this learning rate. So how to control this learning rate? Should we say, so obviously it should be very careful for determining this learning rate. So sometimes it may be very, very tricky to convergence. Sometimes initially maybe the learning rate is more, but slowly we can reduce the learning rate. So obviously graphically we can easily illustrate this by example. So just look, so suppose this is a non-convex function. So here if we consider as the initial point here, so obviously we consider the negative gradient of this function, and then it moves to a positive direction. So obviously we reach next point, and again we reach another point. So in this way, again we move to the negative gradient, because here the gradient is positive, so we go to the reverse side, and so we can get that point, and that may be the global optimum point for this case. But if we don't consider that point as the initial point may be other place. So in that case, again, if we move to the negative gradient, but we can start in some global minimum. So you just look, so we can start in some global minimum. So that is the main disadvantage of this gradient descent method. It is one dimension, and if it in higher dimension, so it is much more difficult because there are several directions we can go to the negative gradient in different points. So obviously, the second point is the learning rate that already I told you. If we consider the learning rate is more, so we can go away from one part to other part, that means one local minimum to other local minimum. Again, if it is very slow, then obviously the process converges, the convergency rate is also very slow. So for that, people are using different other types of gradient technique, that is stochastic gradient approach. So obviously it is advantageous that the gradient approach, it takes much less computation with the gradient-based approach, and for large data set it can be faster because we are dividing those samples into different mini batches and we can take their expectation and solve by similar way. For hyperparameter, because in the previous gradient-based approach there are hyperparameter is weight, initialization, number of states and learning rate. But here another two hyperparameters is introduced, so that is batch size and data sampling, because some statistical way we can consider it those. Theoretically, here there are some local minima and global minima. So theoretically, here we design this as this L function as the expected value of L plus lambda into RW. This is the regularization function. So similarly, we can determine the corresponding gradient function. So obviously, here also there are some problem. What is the loss change? What if loss changes quickly in one direction? Because there are several features, so it's high dimensional problem. So maybe if you go one way, so then you can the gradient loss is less. In other way, the gradient loss is more. So in which direction you should move? So there are different things. Also, there may be some saddle point. So because if in high dimension, if you are in valley, so that means if we move anywhere, any direction, so always there is not that much of less gradient. So how to move? So that's why again people are designing other different types of algorithm, that is stochastic gradient approach with momentum. So obviously here the basic concept is, suppose you have a ball on the air surface. So the location of the ball in the horizontal plane represents the weight vector. So obviously in that case, if the ball is stuck in some saddle point or another way, so because there is a momentum, so that means there is a velocity component, so that can help you to reach the right direction. So obviously the concept is given here, so maybe some rapid oscillation is there. So anyway, so mathematically it can be represented as, you just look in stochastic gradient is basically the iteration scheme is this, xt plus 1 is xt plus alpha into grad ft, so where alpha is the learning rate. And for the case of stochastic gradient momentum, so there is a velocity component vt plus 1, and two parameters are there, one is learning parameter and another is moment parameter. So by using these two, we can determine this iteration process, that is xt plus 1 is xt plus vt. So this is the displacement term and this is the velocity term. And obviously, initially people are considering these two are same because maybe SGT plus momentum formulates in different way, either this or this, but they gave in the same sequence at some stage, obviously. And here initially we consider this moment parameter is less, but slowly we increase it near to 1. So again, there are some difficulties with this stochastic gradient method. So people are considering different better moments. Say this one another example. So conceptually here they use, because of there are two vectors, one is displacement vector and another is velocity vector. They just consider their resultant vector and consider this as a for the iteration scheme. Anyway, so these are very similar. So there is another method. This is very important. This is known as AMSE. So here the concept is you have a scheme of that weight vector theta t is theta t minus 1. This is the learning rate. So but this learning rate is variable. So they consider this learning rate as for each parameter, because this vector has different parameter, weight parameter. So consider this wp plus 1 is w2 into theta w gt. G is basically the gradient part, And then this ITER W is defined by this ITER divided by sum of the squares of the gradient. So this is summation of the squares of the positive derivatives. So basically, here individually, we are giving weights to all the weights of this weight vector. So individual adaptation of learning is important here. So obviously there are some other approaches. I just skip all these approaches, but there is a table. Just look. If you consider the different approaches like SGB plus momentum, method of adapt lag, RMS pro adapt. I am not discussing these two. But the thing is, here just look is obviously in the fast case there is no transfer fast movement. Here the SGB plus momentum, there is a tracks of the fast movement, so here we use the moment. And second case, we consider both moments and adaptive learning rate, and similarly, that already I showed you, similarly RMS pro and adults, they consider the other components. So, and basically we are working on the second order optimization, but this is difficult for determining those error terms and other things that the convergence rate is not so fast here. So here basically we consider a very simple second order Taylor expansion where this is the first derivative part and this is the second derivative part of the linear matrix. So this by Newtonian approach, this W star is represented by W0 plus HW into the inverse of gravity 0. So here we use this Hessian matrix and gradient both, but computationally it is much more difficult first order approaches. Anyway, so this is the conclusion of our presentation. So optimization is closely tied to this generalization of AI in machine learning approaches. And the number of local minima, this is a very important point, the number of local minima grows exponentially with the number of parameters. That means if you have your model parameter is more, that means number of features is more, then obviously those local minima increases, so then it is exponentially grows the complexity. So different local minima generates different extent. So in general, if there are small data sets, maybe 100 case examples are there, or maybe a little bigger also, but without much redundancy, that means data don't have outlier and other things. So redundancy is less. So in that case, maybe you can use the simple approaches, that means gradient approach or stochastic gradient. But on the other hand, if there is a conjugate gradient and other concepts, for the big data sets or where the data redundancy is more, so that means there we use divided those data sets into mini batches, and maybe we can use those advanced approaches. So with this, thank you all. So these are the references. Maybe these two books are very important. We can go through those books, those basic mathematical optimization part you can take. And some other important papers, references are here.
Any question?
Thank you for your attention.
Any question?
Black question.
Sir, actually, in these types of problems, when you have some very particular problem, you need to make several iterations for some chosen number of step size. And after solving all of the sub-problems, you decide on one particular number of step size, which gives the minimum iterations. So now, in a stochastic problem, when you are dividing a big problem into many sub-problems, each of the sub-problems has to be solved for different levels of step sizes to ensure that we get optimal.
Not always. Maybe initially we consider this is same step size, but if we consider one step size is different initially, there is a very big problem.
Right.
Yes. So that's why initially we consider the all
the sizes
we consider the samples from the same data set.
So actually, that makes sense because otherwise the problem won't do it.
Obviously, these are some classical approaches. All the cases there are some pros and cons.
Right.
So obviously, as per the data set, as per your model, so you have to think. So which algorithm? Sometimes they use some combining two approaches. They are some hybrid type of model they can design. So obviously, because here you have to understand physically what is your problem, what is your data set, what types of data are there. So then you have to decide. Not always just start with basic.
Thank you.
I have a question. Suppose your model contains 10 parameters. So you have used one is a hyperparameter. So does it mean among all these parameters, some parameters gravity or impact is more, that is why it is called hyperparameter?
No. Parameter, hyperparameter are two different things. Parameters means those things are involved in the model. So that means in the neural network you are considering that weight vector. So these are the parameters. But hyperparameter is what is your batch size, what is your initial weight vector, and maybe.
These are also parameters.
So because that are not directly involved in the model, so that's why it is called hyperparameter.
So those parameters are not directly involved to the model.
Thank you.
Thanks for this nice topic and presentation, sir. So what I wanted to know, if you take a sample from a population, and if I take a function of the sample, it may be unbiased,
Yes.
but it may
So
have.
that's why I told you initially consider it's independent.
All the samples are IIT. So if you take a function having zero bias, but having more values, and having more bias and less values, because those who are having bias zero may not be good for some of
We assume that error part having bias 0 and variance sigma. So it is assumed it follow a normal distribution with zero mean and small variation. That initially yes.
What about the analysis? Some of square analysis. If I take that some of
This is
square
the
analysis.
total error. So initially we assume say y equal to fx plus epsilon. Epsilon part is very small error part. So now we assume this epsilon follow a normal distribution with zero mean and sigma standard deviation. So then we determine the error in the whole data sets.
So which one we have to prefer? Having less risk?
No, because it's not a single objective model in that case. Obviously, you have two objectives. Always you are trying to minimize the error and minimize the bias and variance. But the thing is, mathematically, if bias is increasing, that means complexity is less. But if variance is increasing, complexity is low. But you have to optimize things, so that's why you have to compromise these two.
So you have talked about some Bayesian information.
Yes, there are some.
Have you tried?
Yes. Bayesian approaches is also one of
So
them.
can you give us some papers?
Okay. So maybe I will.
Thank you very much. Any,
Thank you, sir, for your nice presentation. My query is, are we using stochastic model in multi-objective case or single objective?
Nowadays, people are working on bi-objective machine learning modeling.
Okay.
Working on bias variance instead of they have used two objectives and using some multi-objective optimization algorithm for solving the problem. And in some cases, they are making some cross-validation part. They have used different types of multi-objective modeling. So many machine learning modeling nowadays people are using multi-objective optimization tool also.
Okay. That means that we are using gradient descent method for single objective or multi-objective, and we included machine learning also there.
Yes.
So the same technique can be applied to multi-objective as well. The same technique, or this technique is for multi-objective.
No.
We are using gradient descent together with the supervised learning and machine learning.
Gradient descent is for single objective problem, but there are many multi-objective optimization approaches like Pareto optimization.
Yeah, I am working on multi-objective.
On several multi-objective evolutionary algorithms also nowadays people are using. So,
Can there be deterministic model?
if we develop your model as multi-objective problem,
Yeah.
so then you can use any multi-objective optimization algorithm for solving that problem.
My meaning is, can we join this one to multi-objective?
Yes.
Okay, I will contact you and have a better idea of this. Thank you, sir.
I guess your presentation assumes global analysis. Suppose what will be the bias if you have a record that splits the domain, if you are sure that convexity condition holds over the splitted domains, what will happen? It will bias. You don't understand? Well, I guess you are talking, when you have a domain, your analysis that you have carried out is on a global basis. Suppose you split the domain with the assumption that convexity holds over the different segments. What will happen to this bias?
Obviously, that theoretical concept is not clear.
Okay. Well, finally, what do you mean by what's the characteristic of the Adam or Adam that the strategy that you put last, which looks optimal? So what are the characteristics? The features of the Adam strategy or the movie bias that you present. What are the characteristics?
It's a platform for collaboration. I mean, we got someone now who wants to collaborate.
Yes.
That's why we are here. Open your doubts and collaborate.
Can we extend this stochastic model into uncertainties? Uncertainty. Can we extend our stochastic model into uncertainty?
Yes, uncertainty model also. Because there are similar uncertainty-based approaches for solving this type of there are some easier models and other different types of possibilities.
I'm looking for uncertainty.
And we are talking about
Thank you so much, sir. Now I would request Professor Anusandhan to illustrate. Thank you so much, sir. Thank you, everyone. Now, I would request everybody to go on the second floor for the lunch, and we meet here at this 1:30 for our oral presentation session.
Excuse me everyone, we have a delay in the lunch for 10 minutes. Kindly bear with us. 10 minutes delay in the lunch.
Lights are reflecting.
in our department, sir, both of them. Both of them are in our department. Quick. I forgot. She's my supervisor. Joking, don't cry after I leave. She has already started. She has already started.
It's always
Never. See, her voice is cracking. She has already started. I know firsthand.
Everyone please, while we are waiting for the lunch, can you kindly assemble on the stage for a group photo? Please assemble on the stage for a group photo.
Very crowded. Sir, please
କେତେ ଯିବି ଯେ ସେଇଟା ନାଇଁ ମୁଁ ପଠେଇବି ପା ଗୋଟେ ଲିଙ୍କ ପଠେଇବି ଯେଉଁଥିରେ ସମସ୍ତେ ଅପଡେଟ୍ ଦେବେ ହଁ ସମସ୍ତଙ୍କଠୁ ମୁଁ କଲେକ୍ଟ କରିଦେବି କମ୍ ଥ୍ରୁରେ ସେଟା ଦେଖାଯାଉନି ଇମ୍ପୋର୍ଟାଣ୍ଟ ନାହିଁ କିଛି ଦେଖାଯାଉନଟା ଇମ୍ପୋର୍ଟାଣ୍ଟ हेलो चलती गोटे मीटिंग टाइप अच्छी तो काली आज जाए पूरा कम्प्लीटली व्यस्त माने 3 दिन है लगातार व्यस्त है मुझे जाए ये बसिकी बनईदेव है ना आज सारिदेवा कमटा आज अच्छा
इन सबसे ऊपर उठ चुका हूँ।
अच्छा माने दुकान आज बंद रहिबो अच्छा 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 मो गोटे काम खाली करिवे मोर ऑलमोस्ट केते कुछ
in the presentations. So the few of the part it was already discussed by chairperson right now. So just recall what we had. So metabolite functions, the cost of Swedish mathematicians who introduced the metabolite functions in the 1903, and it's the generalizations of the exponential function if I put k is equal to 1. So you get the exponential series. So it's a generalized form. Then the women also developed in the 1905 with the taking two parameters, and that was E case I, it is represented by this one. Then the further Prabhakar, he more elaborate by using the generalizing, by using the additional parameter, right? And later the Shukla and Chauhan also established these results. And Khan, it was introduced by this the additional parameter by using the certain properties, certain convergent conditions. And Mazarullah also developed the basis of this the meta-Leibler functions. He developed the generalized ML function in the form of this Q form. And the later Bhattacharya also introduced. It is showing in the equations. I'm sorry, due to some technical errors, when I modified in the latex, some equations it has been removed. So there are some extremely sorry for that. So then we look about the basic definitions of the beta functions and then the right generalized functions, which we are getting in the corollary form in special cases. And one more thing which is required in this presentation is the Harvard product. So basically, this Harvard product is splitting the two functions in the product form. So we, whatever we derive the result, we split into two different function form in the product. So we use this Harvard product property. Then the pathway integral, fractional integral. As I mentioned, it was investigated by the Nair with the pathway model which is described by the Mathai and the Mathai Hall, right? And there are many researchers they have been doing using the pathway fractional integral operators because of the large number of applications in the field of in the science, engineering, even though right now in the economics also. So here. This is the pathway integral formula, right? Where the dB is a function effect defined by this one, right? And the pathway probability density function it is showing in this equation number 5. And this operator is also the generalization of the left side of the Riemann fractional integral operator. So if we apply the limit xi less than 1, this pathway fractional integral operator it will convert into the right side of the Riemann fractional integral. So and if we replace xi by more than 1, and it is a generalized beta type 1 or 2 functions, and when it is xi tends to 1, then this will convert into the Laplace form. So these are it is showing in this form. So when xi is more than 1 and 1 minus xi, if you are taking in this form, then this will express in the form of the generalized type 2 beta functions. When you put xi is more than 1 and xi is equal to 0 and a is equal to 1, then the pathway fractional integral operator will convert into the left hand side of the Riemann fractional integral. So, this two theorems we have used here. We applied the beta of my squares. We applied the pathway integral operator in the Q function. So, with this conditions, when we apply this pathway integral operator, so you can see it will split into two functions. One is the form of the Q and another is the right hyperdeterminate function. So, we use the equation of 3 and 4 when we apply this Q operator over here. Then by assuming A1 into 1 minus I by x by y and adjustment of the some limited indications. So we will get in this form, and then we use the Hartman product here. Will get the required results. So this is the main result, and with that obviously we use some corollary to by assuming some suitable values in the parameter. So we are assuming rho xi theta mu sigma equal to 1 and xi less than 1, then the result in the form of the Hartman product, comes in this form. So the parameter has been reduced here, so we got another result. So the original result was this one. So where we have the 5 and 10, 11 parameters. So when we apply this conditions over here, so it will get the form, the product form in the form of Q and 2 psi 1. Similarly, if we apply rho sigma xi mu rho equal to 1 and r equal to 0, then it comes in this form. This part will convert into the extended methacalculable functions, and we are getting the product in the form of the methacalculable functions and the right hypothetical functions. Similarly, when we apply these conditions, then result in terms of we are getting in the form of the right hypothetical functions and the methacalculable functions with generalizations. So these are some cases we applied. In all the cases, we are getting the product form. This is also in this form. So the another terms we have when the limit k is xi tau mu cdn comes to the complex number and xi more than 1, we have taken the conditions. The previous one is the xi less than 1, other one is the xi is more than 1. Then this the path-changing operators, it can be expressed in this form. So again, using the equation number 3 and 6, the equation has been changed because due to some missing the equation numbers, it is taking the previous one. So using this property, and assuming minus a times of xi minus 1p by x by y, and then adjustment of the limit and indications, it can be expressed in this form. So it is here, you can see it is showing the beta functions right now. So when we apply this one, applying the Hartman product, and we are getting the result in the last equation. And we use the corollary based on this term. So by assuming sigma xi eta mu rho equal to 1 and xi more than 1, the result in terms of the Hartman product, which is showing in this equation. Another condition is when we apply this limit, we get the Hartman product in the generalization of the methacalculable functions described by the phi and with the right hypothetical functions. So these are some results which is already developed by some other authors. So we are getting the product in the form of the hypothetical functions and the another extended generalized methacalculable functions. Now another third case, when we apply this r is equal to 0 and xi is more than 1, then we are getting the product form again. So the results we are getting in a similar manner by substituting the different values of the parameters. So this is also showing in this corollary also. So here we are getting the result again. So we are expressing in this form with xi more than 1 condition when we applied the path integral operator, and the previous term we used xi less than 1 condition. Then the pathway transform. So the generalization of the gradual transform and other integral transform like Laplace and Magic. So in this section we define the pathway transform of the generalized Q function. So for the pathway transform of the both the types, it is obtained by using the pathway model, which is developed by the Mathai and Howard. And the Kumar, it is also obtained the type 2 pathway transform of some generalized special functions. So this is the entire equation is the pathway transform, where D is this one, showing the equation by 11. With these conditions, and the pathway transform of both the type is detailed in the space areas containing the Lebesgue measure. It is showing in the last equation. And the kernel function of the gradual transform, it is initiated by the gradual 6. It is showing in this form. And the type 2 pathway transform of the generalized Q function is given by applying subsequence lemma. So this lemma we use for getting the P transform of the generalized Q function. So when we apply this Q transform with this condition, then we are getting the result in this form. It's again the product of the two functions, 4 psi 0 and the generalized Q function. So the proof of we start with the P transformations formula. So we use the P transformations formula over here. Apply this result which is showing in the previous equations, previous slide. Simplifications, then change of order of integrations, and by putting the suitable substitutions x3 y2 minus w is there, and simplifying we are getting these equations, and again for the substitutions we are getting in this form, and using the beta function we require we get the beta elements. So these are the parts. So the similar pattern we can obtain for xi less than g. So the results are more or less similar we are getting, but the aim how we use this is the basic fundamental part. This is not the pure research part. This is the basic fundamental how we use the path integral transform. How we apply in the special functions like the Q function, hyperdeterminant functions, Pythagorean functions, and dimensions. These are the things.
Thank you very much do you have any questions? So that representation, the generalizations of exponential function, the fractional and all the propagating. This particularly how this P transform helps to apply on that tag level, generalization tag level, you are generalizing.
Yes. So P transform, we can apply the Pythagorean function in the P transform, and I think it is already applied by a few of the authors. One, I think the name is from the Kerala, Kumar. He used the P transform function and he developed the transformations of the different functions.
Thank the speaker for his talk. Thank
Thank you so much.
Thank you, sir. I request Professor Anusandhan to please felicitate him.
Thank you, organizers.
Once again, thank you, sir. Next with us is Professor Jaya Gupta. She is an associate professor and head of department in science and liberal art in J.K. Lakshmipal University, Jaipur. So I request her to give her presentation.
Very good afternoon. I'm Dr. Jaya Gupta, Associate Professor in Mathematics at J.K. Lakshmipal University, Jaipur. Specifically, my field of research are special function, integral transforms, statistical data analysis, and now I started working on machine learning. So today I'm presenting my work on machine learning basically. So I have chosen the topic unveiling startup dynamics India in the global context. Actually, startup is nowadays a buzzword. Everyone is talking about startups. So is it really something new? Long back also, we had many startups, many successful startups. But this term has, in this hype nowadays. But how? So, in this particular paper, I have analyzed all those things, why we have this hype or this buzzword nowadays, and how we are going forward, and how it is useful for us in a global context. So my presentation will be
If the cursor is there in that.
So basically startups are small scale companies which are very young, innovative, and have a scalability. The growth aspects are very high. And we all are actually familiar with the startups. So how I will go in this particular presentation is, first of all, how we as India working in this field. What are the challenges and how we are dealing with those. Then analysis of state-wise growth. How each state is working and where they are living. So specific sectors I have taken or specific categories I have taken to showcase the whole analysis. Then how we are performing in the global competition. And basically I have focused on the growth, not the overall number, but the growth aspect. And then finally the future prospects. What are the future predictions on the basis of using ML? So in India, startup ecosystem had an explosion around 2016. Why? Because government, intervened or started supporting startups through various schemes. So initially also we had startups, but when government started supporting these startups, the ecosystem suddenly, scaled up and exploded in a growth manner. So there were few schemes. Actually, there were many schemes, and I have mentioned few like Startup India Initiative, Atal Innovation 2016 that they have come up to a bigger number in just 1 year, 2017. So, what I want to show here is, yes, we have youth, we have ideas, we have innovations, but the intervention of government is equally important. Unless we have the government support, we can't move forward. Now, the second thing is incubator support. Incubators are the, supporting agencies, supporting in terms of financially. So here I have focused more on government incubators because it was very difficult to get the data of private incubators. So incubator support is again one parameter which actually supports this startup ecosystem a lot. So we can see here I have taken the data from 2018 to 2022. Wherever we have a higher incubator support, in later slides you will see those states have performed very well. So now I am focusing on a state-wise analysis. In a state-wise analysis, I have categorized the states in 3 categories. First is the states which are consistently performing well. Second is the states which are improving. And third, which are underperforming. So I have taken examples of 2 states in each category to showcase the whole impact. So, consistently high performing states, we have Gujarat and Karnataka. So, this red line is actually showing the ranking. You can see Gujarat is consistently at rank number 1 from 2018 to 2020. Karnataka, second position, 2018 to 2022. And the incubator support is consistently increasing. The number of incubators are consistently increasing in both the states. Second is improving states. So, in this, as per this particular study, we can see the in the category of improving states, these 2 states, Punjab and Tamil Nadu, have shown a drastic growth. And we will analyze later on what were the actual factors, how they could improve. So here you can see initially Punjab was at a rank around 18, while in 2022 it moved up to 8. So here I have shown the ranks, the rankings, and here is the number of incubators. So these bars are showing the number of incubators and red line is showing the ranking. Similarly, Tamil Nadu, which was around above 18th rank India-wide, and now in 2022 it was at 4th position. If I talk about the initiatives, so after the analysis, we could come up with these 4 major factors which we found common in these states. So, we can see a proactive mechanism which provides holistic and comprehensive institutional support is a major factor for growth of such ecosystems. It's not just a startup ecosystem, but the overall business ecosystem. Then launching R&D. R&D is very important and supporting the new ideas through hackathons, or many such platforms. Then developing modernistic policies in support of innovation. This is again very important. And specifically I have mentioned one factor for Gujarat state because this was a kind of unique factor and I found Gujarat at the top of everywhere. That's why I have mentioned this factor. Gujarat government has launched Heart Start. This is a scheme, Heart Start, to enable women entrepreneurs. So it means when we launch some schemes, such as schemes to empower women, to empower youth, definitely we can see the impact here. Here are some underperforming states I have So no doubt, bureaucratic hurdles are the main. See, when central government starts any initiative, it starts for whole India. But the role of state government is equally important whenever we talk about developing any ecosystem in a specific state. So these are some prime factors which, as per our analysis, were the hurdles for improvement in such ecosystems in Bihar and Haryana. Overall analysis, we have to focus more on R&D. We have to simplify bureaucratic hurdles. We have to support in terms of incubators. We have to encourage incubators to support startups. Now, what is the position of India in global context? So here, I have taken 4 other countries as per the GDPs. I have focused on the countries which are at par in the global GDPs. USA, US, Germany, and China. So USA, China, UK, and Germany, and have analyzed the position of India with respect to these other 4 countries. So for this analysis, we have categorized the whatever data we had for incubators, for field support, for numbers in 3 stages. One is seed stage, one is early stage, and then it is late stage. So whenever we have a startup ecosystem, when we fund a startup, there are 3 categories of funding. One is seed stage, when we are funding any startup in its inception years, and then it is early stage when they are they have started, but still they are in their initial years, and then later stage when they are developed. So on the basis of, we have analyzed the CAGR from 2016 to 2022 for these countries, and we found, although in total numbers US is far ahead from all other countries, China is number 2, but when we talk about growth rate, then UK stands first and India stands second. It shows there is a great scope in startup ecosystem, in startups in India, because we have innovation, we have that caliber. But the thing is, we have to scale it up. This is for early stage. Again, UK is number 1 and India is number 2. And this is last stage. Again, UK is number 1 and India is number 2. Only seed stage funding, we could find that USA was standing at number 1. Still, India has maintained its position in seed stage also. This is overall growth. Overall growth maybe we see India has kept a very good position. So no doubt government initiatives are important. At the same time, we have to simplify many other issues. So I'm simply moving in fast. There are some issues with China's policy. Because of that, they are declining in terms of startups. Now this is the prediction which we have done using ML. So as per the data of 2018 to 2022, this is the prediction for number of startups in India. And this, which is very important, is the number of jobs we can expect from these startups. So it's not about a buzzword. Actually startups can contribute to our GDP, to our economy, as well as they can provide a solution to unemployment also. So we have to, take measures to actually improve this ecosystem for our overall well-being in the country. So I'm leaving the last slides where I have mentioned some conclusions in detail. Thank you. Any questions?
Area. Do you have any questions? Yeah. Yes, you can come with them.
Yeah, so we were talking about model prediction, but like what model will you use? Like what algorithm will you use for the predictive graph?
Actually, we have not used any inbuilt algorithm. We have done using regression, multilinear regression. We have mainly focused upon.
So it's basically linear regression.
Yeah.
So it can be categorized more as a statistical model and not ML model because
yeah,
it's not really ML.
but in some analysis we have used algorithms. So that's why I have categorized it as ML.
And what you said multi-factor linear.
Multilinear analysis.
Okay, so what other factors did you consider while producing that? Only the number of startups?
For India or global?
For India.
For India, actually, we had around 20-25 parameters, which was a bit difficult to analyze. So, using factor analysis and correlation matrix and all other factors, methods we have, we, scaled it down to 7 factors basically. Per capita income, then state GDP, then literacy. I can just a minute. I had the number of what parameters we have used that I have.
Yeah, for the prediction of future startups predictions.
Okay, for the prediction of number
The
of
forecasting you showed that the number of startups growth in future years. For that one.
For this, what we have done, we had data for registered startups. We collected data for unregistered and private incubators supported. See, we had 2 types of data. One is government registered, one is registered but supported by private incubators. We had to mingle up the data, we had to mix up the data, and then we have predicted the growth.
So it's basically based on just the number of startups that are registered or unregistered or funded or not funded.
Prediction is based on numbers.
Nothing, no other parameters is included.
This number prediction is based on numbers, but the analysis is based on many parameters. I thought you were asking about the analysis.
Okay, so
Yeah.
after the
definitely we can discuss. In fact, I will be able to show you the analysis.
So, thank you very much for the
Now I would request Professor S.P. Mishra to please help me. Sorry, it's S.R. Mishra.
No.
Thank you, ma'am. Now for the next presentation, I would like to call Professor Umesh Chandra Nayoda. He is in Department of Mathematics of HNV, Garhwal University, Uttarakhand.
Thank you very much for organizing inviting me here. In fact, such a nice gathering. So, just you have listened the several talk here. So, yesterday you have also listened the talk of and so it will be easy to me to explain the concepts for you. So the topic of my talk is on 6.3 on finite products of materials. Yeah. So, with the like Banach represent principle Maxwell's key proves the fixed point theorem for the system of n map on the finite product of materials. You know that for just to find the solutions of a equation, so either you have the unique solution or the so many solutions. So the Banach construction principle that is very famous for the application in this area. So with the view to generalize this method, we create this result for the product of multiplication. So we will discuss some generalization or some new results about this method sequence. So this fixed point theory is an exciting area of research in the field of non-analysis. This theory has been revealed as one of the very powerful and important tool in the non-linear analysis and has tremendous applications in various branches of mathematics. The concept of the fixed point plays a key role in fixed point theory and results concerning the existence and properties of fixed points are known as the fixed point theory. So yes, you can see here that if you have any map from a set y to y, and then if this map fx is equal to x, then this is called a fixed point. And these are the examples here we have given that how you are, this first example here you are getting more than one fixed point, and here in this example then f has unique fixed point, here this is the second example, and the third one then this f has no fixed point. So now one thing is that if there are some problems that somebody have some function has a fixed point, some has no fixed point, and some has the more than one fixed point. So now in all, in this fixed point theory that we are doing that, how we can get a fixed point, in which conditions, the conditions we will apply on this space, and then we can get a fixed point. And that fixed point, if that fixed point is unique, so then that will be the very good result for this. So in this direction that initially, you know, that the Brouwer, he gave a result that a continuous map on the closed unit ball in Rn has a fixed point. So this result is the topological concept for this. But now in the metric fixed point theory, this we mainly focus on this on the metric fixed point theory, and that is the Banach theory. For the multi-value map, the result is given by the Kakutani, and this Nardler, Martin, and so many other authors are there. So here there are so many generalizations. After Banach expansion, there are several applications for that. So due to its applicability, there are several generalizations of this Banach construction principle. One of them is this neat clear construction principle. Here we just gave the condition here that this F is the map, complete metric space, and F is the map on that. This epsilon greater than 0, there this delta. So this is for condition for that. If this condition is satisfied by the map, so then you may have the unique fixed point. And then there are several generalizations of this neat projection principle. Later on in all these maps are probably, these results are called a single map. But now in 1976, so the youth gave a very important result. This is published in American Map Monthly. And then he takes the two maps. One is the F. It is FE&T two-cell map on the metric space. YD, such that this Fy is subset of this Gy. And this Gy is complete. So he lacks the completeness condition. on the meeting space, only taken the completeness condition on 1. And this is the contraction condition for that. Then you have initially this fz is equal to cz, and if you are taking that the commutativity of two maps, then you will get the unique fixed point. So this result again has so many important generalizations, applications. So later on in 1976, McCloskey generalized the Banach construction principle, and that is for the product of metric spaces. So that initially we have taken this result for the work, and these are some notations which McCloskey used. These are the N matrix with the non-negative entry. So initially, when the constants are defining like this, so this CIK is satisfying this type of conditions. So then this equal to load, this summation AIK RK is less than R for K equal to N equal. And then the head equal to solution R1, R2, Rn for the following equal to 4. So if this condition holds, then this will continue this type of solution will get. So he gave this result. If you have the xi di that I vary from 1 to n, these are metric spaces. So and this is the contraction condition. This contraction condition holds, and B is the constant AIK defined in the previous equations. So then you have a fixed point over this system of equation. We have a unique solution. That is xi is equal to ti x1 x. So here you have the different matrix space x1 to xn, and you are getting this result. So this result is very important, but this is not so easy to understand, and it has also applications. You can see here is figure of Valedictory, and we use this result for finding the solution of integration. Later on, this result is generalized by Zermig for the multivariate map, and then this is also taken by Singh to Siksha, and they combined the result of McCloskey and Zermig. And they taken the two maps here on the left hand side, and they have got a constant point for the result. And now, then we have a result that when you are taking the map from two maps from one side, and if we change this condition here, we extend this for the three map. So then we have got the results for the three map, and we have for the system of equations have a unique solution. And in 90, after that, now there is the problem that how we will get the fixed point for two system of maps. So then we define a new definition, that this is the coordinate wise commuting maps. If you have the two set of maps from this, if you are multiplying this x1, x2 to xn, and then you are defining the map from this x to xi, so then the coordinate of the commuting maps are defined like this. So we have given the examples, and this result is very important that we have given that this result for the coordinate wise commuting. And later on, there are so many, because you know that there are so many meeting forms for the commuting maps. So we have defined also the coordinate wise weekly commuting maps. This is the definition given by us, and this is the example for that. This is coordinate wise weekly commuting, but not commuting. And after that, this result also extended for the four maps with this coordinate wise weekly commuting map, and then we are having the unique fixed point for here. Then we define the coordinate wise asymptotically commuting maps. We reduce continuously we reduce the conditions for that theorem. And on that basis, this is the result which was proved by us. coordinated by RVD committee. We have also given here this definition, and then by generalizing the definition of this RP part, and then we have made some results here for this, for the 4 maps. So just you can see here, there the coordinated by BD committee maps are coordinated by RVD committee. However, coordinated by RVD committee map need not be coordinated by BD committee. So the following examples will verify our concept that this is not the reverse committee. So this is the example, illustration of example. So just you can see here how you are defining the linear system of map, and we have also proved some result from the product of the Banach space. Initially we have taken the result from the product of the fitting space, and now we have taken the result from the Banach space. So there is little difference between, because here we are taking a subset of the this X and these set are the closed, where the C is the product of the C1, C2, Cn, means each C1 is subset of this X1, C2 is subset of this X2. And we extend the result of Gregor's for by using this coordinated RVD committee map, and taking this TI is continuous and linear. And now later on, we have, you know that this continuity is very strong property. So, Professor R.P. gave a result that there is a reciprocal quantity which is not continuous. So we have formulated this also for this product space, this reciprocally continuous map. And we have also given the examples of this one. This map is reciprocal continuous but not continuous. And then we have got the result for this. And there are several extensions for this later on. But basically, the initial thing is that we are taking the different form of the commuting maps. Yes, this is the result also for that. This is an example also for this. And now this is remark that the above definition for n is equal to 1. When you will take the n is equal to 1, so you will get the standard definition of the commutativity. And for also for the asymptotic commutativity, commutativity and for all. So next we have proved some common fixed control for this system map using the concept of coordinate basis. So this is the result here. This PIX is subset of this TIX intersection SIX, and all the other conditions are the same. Just you are taking this coordinate by BB reciprocally continuous. And further we have also, just you can see the remark here when we are taking the result. So if you take especially P is equal to 0 and this SIX1 is equal to this one is equal to 4, N is equal to 1, and the second condition. So we will get the result of U. And the second condition, if you will take here P is equal to 0 and this Sx1 xn, Pix1 xn is equal to xi, so we will get the result of Maxwell. And if we have this B is equal to 0 and N is equal to 1, so we will get the result of ITER. So later on the other hand is there we start with the study of metroscopic fixed point theorem about multiple maps, and we have also some paper on the multiple maps for the metroscopic convection. And one of the result is where for F convection mapping here, this F convection mapping is defined like this, when you are taking the metric space and then T for the F convection is this condition satisfied. So we have proved this result for the metroscopic convection. These are given some definitions here. So here we have defined this for the F contraction of particular type. It is here it is F long where then they are tau long parcel. So that is condition 4. So then this is the result. For that we have to this for the matrix space is F convex result. Just we have taken the conditions defined like this. This X is X1 is the matrix space and this X is the product of space and other conditions are defined like this. So and this is also an example we have given that which satisfy or which illustrate our result. So these are some corollaries for this. So this is the demand that this 3.0 SNPO may obtain as a special case from this result. And the second part taking as YD equal to XI DI, then we have obtained the result of this word over T. So for the application, there are so many applications, but just you can apply this if you take this notice under this bounded solution of the system of functional equations, whereby you are unknown functions, and if I is defined like this. So if you fit these conditions for here, and this L be an arbitrary set, so assume that this Fik, this L to L, I is equal to 1 to L and this Hi is defined like this. So we are formulating this equation. So this Matkowski contraction and then all the conditions are here. So then the system of functional equation is phi I t, Hi t, phi 1, F1 over this T belongs to L and I equal to 1 to L has exactly one solution. So replacing the set by the metric space L3, I am assuming that the functions 4.4 are continuous. One could show that the unique bounded solution must be continuous. Under the assumption that L is the real interval, the integral solution of the system was considered by J Matkowski, also where pattern the line of LP spaces are. The differential solution of the system were treated by J Comenier. And you can see this differentiation also. So these are some results. Why I am interested in this? Here most of the people are working in the applied mathematics. So if anybody is interested for the pure mathematics and especially for the big bang theory, so this is a nice area for doing the work for the newcomers in this field. So thank you very much.
There are a lot of applications when we are putting the mild solution for various type of problems using the contraction map. Yes, is there a unified way to do?
No unified. You are taking the different conditions for the different ways. Somewhere you are relaxing the conditions, somewhere you are adding the conditions.
Questions, so let us congratulate the students for
Thank you, sir. I request Dr. Vilgadas to felicitate you.
Thank you.
Thank you, sir. Our next presentation will be given by Professor O.M. Ringola from Department of Mathematics, University of Lorraine, ITER. So I request you to present.
Oh.
Good afternoon to every one of you. The title of my presentation concerns principles to populate and determine the optimal development. There are three authors there, the presenter and the first author here. Once again, this from Nigeria.
I don't want there first on the top. It's three. Yes.
Okay, that's the outline of my presentation, introduction, methodology, results, analytical, results, numeric, and conclusion. This paper is concerning the method or the conjugated method. One of the earlier speakers has mentioned about that. In this paper. And this method is a preferred method of solving large-scale optimization problems. We have the site where there are collection, it's a big collection of real-life applications from the telecommunication, from the manufacturing, all kinds of sectors that are modeled mathematically. And here, people who solve maybe from their consultancy engagements, who solve some of those problems. So don't get here. Those people are interested in use them as test problems. There are some of them that provide solutions up till now, waiting for people to solve them. And that's why people kept on their toes. There is ongoing research in the CGM. Well, the attraction for the CGM is simply because it has very low memory requirement. When you have a problem that has millions of variables, and that describes the technological staging that we have. Most of these things we enjoy. The challenges are posed in the type of, in the extreme number of variables that have to be determined. And here is one of those things. But like I said, people are struggling to make their contribution because the problem requires speed, accuracy, and reliability. So that's the contribution method. So a number of methods have evolved over the years. So here are some of them. The man who started with the pair of Heston and Stephen, that's 1952, followed by others. Number 9 is the effort of my research group, that's $1,000. Ali and Wisely. Ali works as a collaborator in South Africa. The two of us are in Nigeria. The result of this was presented in ICL year 2010 at Hyderabad. Now, the methodology for this present work started. There are so many approaches. Out of the existing one, I just cited 2. And fortunately, I've been involved in the 2 approaches. The first is to look at CGM parameters, such as descent search method, the search, then the step length alpha, then the update parameter beta. I've worked on improving the update parameter, and that's the result that I said I presented in 2010, So, for another approach is to form hybrids, use a few of the methods and use it to produce other methods, so that we cannot compare efficiency and say, oh, this one is better than all others, or is the best among them. So I also have a taste of that. So, but the problem, the challenge is, there's hardly anybody who is able to produce more than 10. At best, I think I've seen 16 putting this and this and this together, hybridization, and then produce 16. Whereas there's a whole space that has to be covered. So we are now bringing up an approach. So, three-pronged attack. The first one is to populate the CGL space using the concept of mathematics, simple concept of linear combination. Use the concept of mathematical modeling and the data analysis, empirical data. I've spoken about that in this project. So use those to analyze the resulting methods that the population now brings about. Then we use an optimating criteria in the sufficient descent condition of the CGA to use to identify the optimal CGL. So in carrying out this set of goals, those methods that I have shown you, build up a model to generalize all of them. That's what I have beta I. So we want to start characterization. The first is we want to show that the set of classical CGLs, 4 to 13 that I've shown you, spans the space of generalized, the space of CGLs. So let's take a set. That's a 10-member set. I'm coming back. So take a set, B1, B2, B2. Then show that that set is linearly independent. Then can we now also show that this span is a superset of the generating set? So those are the two questions we want to answer. And quickly, that's what is addressed in the proof. Well, the expression 4 to 13 appear in the national form. There's a result that says the quotient of linearly independent sets is also linearly independent, provided the denominator never vanishes. So we use that and we show that that set is linearly independent. The second aspect is, let's look at the span. The span is denoted as set S. So in the paper, we outlined the various classes of methods. I built all kinds of methods that will be generated by using the concept of this concept of linear algebra. That will show that is a superset of V. The meaning is that the populated methods, they are not repeated. They are never linearly dependent on one another. They are separate methods. So that's the result of that. Another one is, how many do we produce? So that's addressed by theorem 3.2. The proof is So we generalize the concept for the generalized method, and then we now use it to show using some existing results. So and then we now find, so that's the expression, the product of those two numbers. Well, quickly, maybe just to show, for the 10 member classical structure, we have produced 1,953 methods. We try to show by substituting the coefficients AI or BI in generalized method. We have tried to show how we can recover the existing methods. Further characterization includes that the update that generalized satisfies the sufficient descent condition. The sufficient descent condition is a kind of saying normalization, that you can normalize the system so that you can control the range of values that they produce. Next, yes, this is very important for computational processes, especially of the iterative kind. In the sense that, is there any assurance that we have solution? Is there the convergence that is answered under that theorem 3.4? Or depending on certain conditions, there will be global convergence. Start at any initial point, you are going to get a solution. That's the guarantee for that. So now we using the set of what I call the empirical data. What's the empirical data? From practical computations, using some of the problems in the pool that I said is online. Some of the problems there. So we downloaded and now test on some of these methods. Then so using the algorithm for the CGA. So we got some results. Now based on that result now, so we now selected a section of what the methods that are generated, both old, existing and new, and said is about 2,000. But I cannot deal with 2,000. So we now took a class out. We call it one by one CGM. What does that mean? The CGM, whose update parameter has just a single term as the numerator and a single term as the denominator. That's the class. And fortunately enough, we have about 48 of them. So 48 of them, they were assessed. Then the parameter for efficiency was given to them. So there are some, all those existing methods that falls, 8 of them, 8 of the 10 are one by one CGM. They have only one term in the numerator and only one term in the denominator. So that's what we have. So we selected the 12 top CGMs, ranking them in terms of the efficiency coefficient. What we have is listed here. So then from here, just to demonstrate the graphical computations involved with these methods. So we selected those 12 and we use what we call the performance profile using the Dunn Moland the Dunn-Moore performance software. So here's the performance profile. Well, permit my software is poorly presented. This for now, that's what I can do. In the paper, I make sure a sharper figure comes out. So in concluding, we have the top notcher solves 76.1 out of percent of the problems that we use to test. Then on and on like that. So, and the implication of that is that method is the optimal CGA in the class that we have selected for demonstration. So, and that's the formula for the CGA that is our optimal CGA. I say, what have we gained? So, where people expend energy plus 16, that's the highest. We have now got, we started, we used 10, and we have multiplied, we have produced it in 200 folds. I think it's an effort that is worthwhile. Then out of that, we have been able to pinpoint the optimal one, so that if anybody is interested in that method that is most efficient in that class, so that's the method, that's the formula. So I think what is left of me is to, okay, so that's the conclusion which I've just mentioned. So we have the references listed there. Yeah. Okay, thank you for this.
Thank you. Do you have any questions? By conjugate gradient method, by CG.
Yes, you know, this is the first step. Now,
GMRS also.
what is it?
GMRS, generalized minimum residual.
Okay, you know, the conjugate gradient method uses something to reduce the residual to 0. And that's the conjugacy property.
Let's thank the speaker for the inspiring talk.
Thank you so much, sir. I would request Professor Ekstrom to participate. A very warm thanks to all our speakers, presenters and delegates who became a part of AMSE 2024. And thank you so much for your words of wisdom. It will be a great pleasure for us to listen to you again in our future events. It was really a great honor for me to welcome you all in AMSE 2022. And now, for closing AMSE 2024, we'll begin with our valedictory session. And for the same, I would request Professor Manjula Das and Dr. Arunachal to please come on the dais. Along with them, I would also request all our speakers and presenters to please come on the dais.
Professor Murthy. Professor Utpal sir. Utpal sir. Sudhika madam.
switch up the projector.
Just a minute, yes.
Light up the projector, please.
शर्मा सर फोटो भी ला जाइए। I hope it's done. Santan sir, हो गया? Thank you everyone. Now I will proceed with the valedictory function. I would request Manjula ma'am, Sunita ma'am to take the chairs on the dais. Professor Murthy, Professor Utpal sir, and Professor Nadeshan, please take the seats on the dais. We would start with the valedictory function. Manjula ma'am, Sunita ma'am, Utpal sir, Nadeshan sir, and Professor Murthy. Please take the chairs.
इनकी सर्टिफिकेट का कॉलेज होगी सेपरेट सर्टिफिकेट एक जगह सर्टिफिकेट 8 को ठीक
अभी तो आएंगे सर्टिफिकेट्स so there will be a long process and to the valedictory. So the most awaiting time of giving the certificates. So first we will start with the best paper presentations. So parallel sessions going on from the last 3 days. So many participants, and we have few sections. We have developed. We had few themes. So based on the themes, we have 7 themes. We had divided into 7 themes. So within those 7 themes, the best paper presenters were selected, and totally all the session coordinators and with the help of session chairs also. So I'm going to take their names one by one. They can come to the dais to collect their best paper certificates. So the first category is for the computational fluid dynamics, and the award goes to Ms. Rupa Baithalu from Department of Mathematics, ITER, SOA. Nadeshan sir, please. The next theme of the session is cryptography, for which the award goes to Ms. Kalila Kanya Parida from NIT Rourkela. Kalinga Kanya Karira. Anyone on behalf of Kalinga Kanya from NIT Rourkela? Okay, so we'll pass that. The third theme of the session is non-linear analysis and non-linear dynamics, and the award goes to Ms. Taiba Zia. And she is also not present. She has given the responsibility to Apul sir, I think. There is Apul sir. Sir, collect the prize of Taiba. Collect the prize of Taiba. She told me. Taiba is gone. Before going, she gave the responsibility to Taiba sir. Apul sir.
On behalf of Taiba, she is very glad. I want to say 2 sentences for her. And she is a BTech third year girl. And yesterday night I am talking with her. She is asking us, if someone gets the best word, what you will do? She is asking if. I said, who is that confident person? So I said, no, just I am asking. If we get, then what you will do? I said, I will send physically. Then I am just thinking, she has confidence. And when she left, and she said, sir, maybe you should observe my presentation. And when I see the mark sheet, then she is there. So, very confident girl.
Her name is Taiba Zia.
Madam, do you know her? No, she leaves because she has a airplane.
Okay, so let her, okay, inform her.
Next theme is numerical methods. For the session of numerical methods, the prize goes to Ms. Siksha Manini Sahu from CDS ITER SOA. The next theme is ODs and PDs and their application, and the award goes to Mr. Chau Valedictory from NIT Arunachal Pradesh. Sunita Madam. Then we have the machine learning and application, which was the largest group, I think. And from that we have Mr. Parisiddha Sharma from Tejpur University as the winner. Manjula ma'am. Sir. And the last group, the last theme is optimization problem, and the award goes to Mr. Mohan Chandra Adhikari from Trivandrum University, Nepal. Manjula ma'am, please go.
Now, before certificate distribution, I would like to introduce Dr. Satyaranjan Mishra, who is currently working as professor in Department of Mathematics, SOA deemed to be University. He has 19 years of teaching experience in both PG and UG level, and he has done his PhD from Siksha Anusandhan deemed to be University. His research area is heat transfer, magneto, hydrodynamics, porous media, etc., with a broad area of fluid dynamics. He has published nearly 350 papers in the international journals of repute. He also took a position of top 2% world scientist by Stanford University, USA in 4 consecutive years. We are highly fortunate enough to have him as a part of SOA family, and for the same I would request Professor Manjula Das to felicitate him. Congratulations, sir. Now next I would like to introduce Dr. Anusandhan, who is the convener of AMSE from last 3 consecutive organized way. He has completed his PhD from Guwahati University, and he is in 8 years of his teaching experience. He has conducted these 2 international conferences. One was AMSE 2019 and another was AMSE 2022. And AMSE 2024, we all are a part of it. And he was the convener of it. So for the appreciation, I would request Dr. Manjula Das to present him with the certificate.
Congratulations and all the best for the all the blessings always to you.
As the co-convener of AMSE 2024, I would request Dr. Manjula Das to please give the certificate to Dr. Mitali.
Congratulations and all the best. And I wish next time you take the lead.
Now we will go to all the presenter certificates. So I will call it theme wise, so be ready, we will know the themes. So first we start with the computational fluid dynamics with Rupa Meghalu. Natasha sir, please. Next is Arpita Viswas. Vinay Kumar Barad, Prashant Kalida, Amit Kumar, Prashant Kumar Sahu, Chaudhary Santosh, Ratna Manjari Sahu, Richa Joshi, and Prabhu Prasad Nayak. claps for the presenters. Prabhu? Absent. Absent. Please, Prabhu. Okay, the next theme of the session is cryptography. I would request Professor Murthy to please give away the certificates. First is Shamli Sharma, Priyanka Agarwal, Priyanka Agarwal, Kalima Kanya, or she is absent. Then we have Shashikant Agarwal, Sanjay Kalima is absent. Shashikant Agarwal, Hosting of the party, Odisha Sasneha, and Ibrahim Yaksan Hassan. The best photographer we have. Next theme of the session, nonlinear analysis and nonlinear dynamics. Utpal Sasar, please give away the certificates. The first is Sayan Manik, Saurav Roy, Balram Pradhan, Sayan first, Sayan, Saurav Roy, Balram, Ishita Das, and Aaron Monaldi. Same continues with nonlinear analysis and nonlinear dynamics. We have Aliyu Abba, Kaneru Gopi Sairam, Aliyu Abba and Kaneru Gopi Sairam, Samrat Datta, Sonali Sahu, Shakti Prasad Mohanty, Arjun Singh, The next theme of the session, optimization problems. The first one is Mohan Chandra Adhikari, Badri Prasad Pandini, and I would request Sunita ma'am to give away the certificates. Badri Prasad, Deepak Babu, Amgen. Nirlipta Mangraj, in behalf of Nirlipta Subhashri Collector. Sachin Wagle, and Vishwaraj Adhikari. Continuing with optimization problems, we have next is Olabde Matthews Banigola, Shakti Prasad Mishra, Subhashri Parida, Smarak Uttam, Prashantini Samal, Prashantini, she's not there. Golam Bihari Panda, and Chandrasekhar Sahu. ODs and PDs and their applications. Manjula ma'am, please do the honors. Kaveri Parida, Shetapatma Sahu, Arya Suman Patnaik, Abhishek Sharma, and Chor Valedictory Sinkai. machine learning and its applications. Ma'am can continue. Prasiddha Sharma. Siddhant Swarup Malik. Smitaranjan Datta. Samiksha Das. Aryan Mishra. Nitish Mathi. Hemant Kumar Kalo. Umesh Kumar Das. Sashikant Prishti. Mudra Narasimha Rao, Vishwajit Kumar Senapati, Gracie Ram, Priyanshu Kumar Bella, Akash Kumar Dwivedi, Binodini Tripathi,
Sir,
yes, you should.
Co-organizer. Co-organizer. Not tired. I'm not tired.
Okay. Supraranjan La, Jitendra Kumar Singh, Arpita Priyadarshini, Giriraj Kaleru, Sharda Kumari, Shyam Sundar Gaura, Devashish Swapnesh Kumar Nayak, Abhinandan Rao, Samvit Ranjan Patnaik, Jogeshwar Tripathi, Anisha Subudhi, Subrat Kumar Nayak, Now I would request Anita Thomas ma'am to join us on the dais. Thank you, sir. Pratiksha Manini Sahu. This is for the sessions of numerical methods. Sudham Bin, Vikas Gogoi, Santoshi Panigrani, Bhaskar Jyoti Bhushan, Abhishek Balakrishna. Abhishek Balakrishna. everyone. That's all for the paper presentation. Now I request the dignitaries to go and take their seats. Thank you, sir and ma'am. Now I request OD Material sir to come on the dais. Sir would give away the certificates for the technical members who have, due to which this third international conference was possible, very much involved. The technical members will get the certificates on the dais from McKinsey sir. The first one for Bhubaneswar sir. Absent. Stanton sir. Dr. Abhishek Das. Alice Chinmay. Dr. Sanjay Mandi. You can take over the certificate. Dr. Vijay Kumar Paikrai. Dr. Santilata Champati, Professor Dr. Anita Panda, Dr. Prakash Kumar Rathore, Dr. Pinanki Prasad Faro, Dr. Anuradha Sahu, Dr. Varsha Priyadarshini Sarangi,
Okay, change, exchange the certificate.
Give it Varsha.
Okay.
Dr. Sobhagya Kumar Sahu, Dr. Kanisha Pujaru. Now Dr. Anuradha Sahu and then Kanisha Pujaru. Dr. Annapurna Panda. Annapurna ma'am. Ms. Sonali Sahu, Annapurna Panda, Dr. Sweet Milan Sahu, Dr. Lopamudra Das, Dr. Sitapra Mahato, Dr. Arjun Paul, Dr. Lambodar Jena, Dr. Shishri Sangeeta Pradhan, Dr. Sudipta Gayan, Dr. Subhashis Bhora, Dr. Pavitra Kumar Pradhan, Dr. Sabeen Kumar Bansal, Dr. Ashish Kumar Pati, Dr. Gauranga Pradhan, Dr. Shubhajit Saha, and Dr. Pavitra Narayan Mandal. That's all. Thank you, McKinsey sir. He has been quite sport all these 2 days. Thank you, Lord sir. And request the convener to give the certificate to our anchor Kumuda Sharma.
Yeah.
He has been doing her job tirelessly from the last 2
Fantastic,
days.
fantastic.
I would request the convener to announce the closure of the ceremony.
Good evening, everyone. And what I can share now, so I cannot express how much I'm happy. So first of all, I want to say thank you to everyone for coming here and present your paper, present your work. I hope you were discussing each other and just blow the the conference of AMSE 2024. And your effort, your presence make this conference a success, and I hope that will continue in coming years, and that I believe that that conference is the one place where we can connect each other, where we can collaborate our work. Okay, that way we can extend our the research community field, and that will help to, that means all the research peoples. That is my belief, and on that belief I work to continue this conference. This is our third conference, and I know this is what we can say. So many pressure is there, but your support is appreciable, because at moment sometimes at the same time all the point is coming and we have to solve, and that times everyone's support is there, and I get this certificate support from all the side, all the members, all the participants, all the respected speakers, and that is why this conference is success. I hope, and that I believe this one, and this I hope will meet again 2026.
Announce the closure of the
Yes. Now, this time to get your feedback, and I will share feedback form as a written, because that will help, that will make more, that means improve our next year, and that is the improvement from, because of your solution, your last 2 years feedback, because in 2019 we were the first organized, and we are totally new, and I am a new faculty in this institute in that time. But still, it happened, and after that, we get the feedback from all the participants and the speakers, and then we take this all the feedbacks, and after that, we try to implement in the next conference. I hope in 2022 we success. 2022 is online basis, and we have published all the paper in the AIP conference proceeding in 2022, and 2019 we have published our paper in Spinzer Nature, and this time. Also, we take all the feedback of last 2022 years conference, and we implement all the feedbacks and try to modify, and upward is very important. So now I am just request to some participants, please come and share their experience, and that will make me happy more, and that will, what we can say, that will make more success in coming in 2026. Okay, please come one by one and share your experience.
Sure.
Respected professors, research scholars and organizers, a very good evening to everyone. I am Vinay Kumar Badal, currently pursuing a PhD in fluid dynamics from JIIT Noida. It's an immense privilege to be part of this esteemed international conference organized by SOA University and NIT Arunachal Pradesh. First and foremost, I would like to express my heartfelt gratitude to everyone who has contributed to the success of this conference, from the dedicated chefs who provided us with delicious meals to the esteemed professors who have made this event truly remarkable. I would like to extend special thanks to Professor Sunita Chandra, Professor D. Makinde sir, Professor Ramchandra Sarma sir, Professor Satyaranjan Mishra sir. Your presence and insights have enriched our experience here. I am particularly grateful to Dr. Pavitra Kumar Pradhan from this university for informing me about this conference. During this conference, I had the privilege of meeting and discussing with Professor Mishra, Makinde and Sarma sir. Their advice and perspectives have provided me invaluable direction for my future research. I am deeply grateful for their guidance. Conferences, workshops.
No more feedback, someone from the Nepal team.
Namaste to all. I am very, very thankful to the organizing committee for this opportunity. From myself and from the entire team of Nepal, we 6 of us participated in this conference, and we got quite strong and hospitality services. Thank you so much for this. Meanwhile, I have to remember my supervisor, Professor Dr. Pankala Havala, as well as late supervisor, Professor Dr. Urmila Pakurel as well. And hope that in the next conference also, we can participate and express our knowledge, ideas, and collaborate with other researchers. Thank you.
Now there is a bit of surprise for all the guests. Last night we witnessed that Western Odisha festival you must all have enjoyed, and there was a delicacy talked about over there, Arisa Pitha. So we have the conveners and we have got some Arisa Pithas for all of you. Just have it and enjoy for the time being, and then we will have our tea break. This is a Western Odisha delicacy.
Why Western Odisha?
It's whole Odisha delicacy. Correction. We love it all. It's all made up of, I think man can jaggery and rice powder.
Ghee. And good.
Good and till. Jaggery or good, rice powder and till. It's a mixture of all those things.
Arisa Pitha. Arisa Pitha.
Arisa Pitha. This is one of the pitha we say.
Sakti.
It is famous in Odisha. In village it is very popular.
Sakti.
Villages.
Yesterday we ate chakuli pitha also.
Dosa we call chakuli pitha. When dosa is different.
Ma'am, please have it.
But this is Arisa Pitha.
In between this, if anyone else from the students want to give their feedback while eating, we can listen to that. Any feedback on this delicacy? Guided sir wants to say something?
नहीं बिल्कुल लेके जा सकते हैं.
Thank you very much for the organizer for organizing such a nice conference.
and especially we are thankful personally that for the nice hospitality and all the academic programs are well managed. Everything is well managed. So once again I congratulate to all the team members of this organizing team and especially Dr. Apule. So thank you very much, and I hope we will visit here again. Thank you.
Thank you, Doctor. Now the three-day international conference, the AMSE, third AMSE is now declared closed. So you can all gather upon the dais for the final group photo. And after the group photo, there is a high tea arranged again in the second floor. Please don't leave without the tea.
भाई धोखा दो Yes, ma'am. Okay. We'll provide you with a pack. Please try. Please inform me. I will give you.
We can stand in the front.
Please come. Please come on.
अच्छे ना सरला सरवाला तो गोटे काम कर जो टिश्यू पेपर अच्छे दौड़ी जाओ मैडम ही इज कमिंग विद द टिश्यू पेपर और जस्ट वेट ओके
Some of you can come over here. You can join over here. They are taking the photo. Hey, take one more. She is there.
पैनल में बैठकर कुछ नहीं जाते ऑलरेडी सेटेड
भी रखा था भी रखा था
मैं इसलिए बोला था कि अगर फोन आता है ना तो प्रॉब्लम हो जाएगा। मैं इसलिए वो वेटिंग में था, मैं वेट कर रहा हूँ तो आपका फोन नहीं आया, तो इसलिए मैं बोला था थोड़ा बहुत आपका बैकअप की कोशिश करेंगे, नहीं तो थोड़ा प्रॉब्लम हो जाएगा।
आप बोले सर मैं उस साइड एक देखा ट्राइपॉड जैसा ही ट्राइपॉड नहीं है
वेट ऐसा नहीं कि मैं अचानक आके मैं बोल देता हूँ तो तब थोड़ा दिक्कत होता है, इसलिए मैं थोड़ा
इसलिए लिखा भी आपको आपकी आँखों को लेना चाहिए, मैं थोड़ा देख लेता हूँ।
व्यूअर कितना था सर?
नहीं तो व्यूअर तो बहुत कम है, कल बहुत थे, कल गाना मजा आता ना।
नहीं मैं वो देख रहा था जो कौन है ये शायद आज चार देखा था एक टाइम।
बहुत अच्छा लगा कि नहीं? लाइव सेशन कैसा लग रहा है फाइनली?
सही अरे वो बैग मिला ना?
कौन सा सर? हाँ आपका, हाँ वही रखा हूँ, नजर के सामने रखा हूँ। हाय बोल दीजिए, हाय बोल दीजिए। हाँ बस ऐसे होता है ना लास्ट में खत्म होने के टाइम। सर हो गया डन। मैं हिंदी में क्यों सर इट्स डन। Yes, it's completely. You can check. It's 95%. Thanks. दौड़ लेगी? ठीक है।
थोड़ा खुल देंगे तो सही
अभी खुल गए?
अब हो गया तो ऑलमोस्ट।
हाँ थोड़ा मैं ऐसे ही कर लेता हूँ सर प्लीज़।
कोई नहीं है सर, ये दिखाएगा तो लोग बोलेंगे कोई नहीं है।
खत्म हुआ ना इसीलिए मैं इसीलिए वो माइंड ऑफ सेशन दे रहा हूँ। जगन्नाथ जी, उसके बाद हम आ जाता है Thank you for watching. मैं पकड़ता हूँ